Watch a friend of yours fall into a black hole, and here is the strange thing, the thing that almost nobody bothers to tell you. You will never see them cross the edge, not in a year, not in 1,000 years, not in 1 billion years of sitting there with your eyes open long after the last star in the sky has burned itself down to a cold ember. Your friend will still be there, hanging, getting dimmer, getting redder, slowing down, but never quite arriving, never quite gone. Frozen at the doorway like a photograph that refuses to finish developing. Now I want you to sit with that for a moment, because it is not a figure of speech. I am not being poetic with you. That is what the mathematics actually says. A fellow named Carl Schwarzschild worked out the equations for this in 1916, and I will tell you where he was when he did it, because it is one of the best stories in all of physics. But the equations are clear as a bell. If you stay outside and watch, your friend never crosses. The image of them freezes at the edge and fades away, and you carry that frozen picture with you until the end of time. And yet, here is the part that ought to keep you up at night, except that tonight I would rather it gently put you to sleep. For your friend, none of that happens. Nothing freezes. They do not slow down. They do not hang at any doorway. They fall right through the edge without feeling a single thing, without even noticing there was an edge to cross, and they reach the very center in about 15 millionths of a second. A snap of the fingers and it is over. So which is it? Do they hang there forever, or are they gone in an eye blink? Because those two answers cannot both be right, and yet the same equations, the very same ones, give you both. Same fall. Same person. Two completely different stories about how much time went by, and they are both correct. Something has to give. And figuring out what gives, that is going to take us to the one place in the whole universe where space stops behaving like space, and time stops behaving like time, and the words we use every single day, words like where and when, quietly stop meaning anything at all. That is where we are going tonight. Slowly. In no hurry whatsoever. We have all the time in the world, which, given the subject, is a funny thing to say. Let me start by taking the mystery apart the way you would take apart any good mystery, which is to refuse to accept the first thing anybody tells you. And the first thing everybody tells you is that your friend freezes at the edge forever. Fine. Let us hold that up to the light and turn it around and see if it survives a hard look. Because in my experience, when nature seems to be doing something impossible, it is usually because we ask the question badly. But before we can even ask the question properly, I have to tell you what this edge is and what this center is, and why there should be any such thing at all. Because a black hole is not a hole. It is a terrible name. It is not an opening, not a tunnel, not a drain in the bathtub of the cosmos. It is a place where a great deal of stuff has been crushed into far too small a space, and gravity near that stuff has gotten so strong that once you get close enough, there is no getting back out. Not you. Not a rocket. Not light itself. And the surface, the edge, the point of no return is not a wall. There is nothing there to touch. It is a boundary in empty space, an imaginary sphere, and its only property is this: cross it and you cannot come back. We call it the horizon, same word the sailors use, and for the same reason. It is the line past which you cannot see. How big is this horizon? That is where Schwarzschild comes in, and his answer is beautifully simple. Take the mass of the thing, multiply it by the strength of gravity, by a number we call big G that Newton needed. Multiply by 2. Then divide the whole business by the speed of light, times itself, and that gives you a distance. That distance is the radius of the horizon. We call it the Schwarzschild radius, after the man, and every lump of matter in the universe has one, whether or not it is a black hole. Let me make that concrete, because a formula floating in the air helps nobody fall asleep. Take our sun. That warm, ordinary, well-behaved star, 1,000,000 times the size of the Earth, so big you could pour 1,000,000 Earths into it. What is its Schwarzschild radius? Run the numbers. You get about 2,953 meters. Under 3 kilometers. Let that sink in. If you wanted to turn the sun into a black hole, You would have to take that entire blazing ball, all of it, and squeeze it down until it was smaller than a decent-sized town. Under 3 kilometers across. A thing you could walk from one side off to the other in half an hour if it were not, you understand, the most destructive object imaginable. The sun is not going to do that, by the way. It is not heavy enough, and I will not frighten you with things that are not going to happen. The sun will live out its long life and puff itself into a gentle glowing cloud and settle down as a warm cinder. But the point is the number. Under 3 kilometers. That is how absurdly, how violently concentrated matter has to be before this edge of no return even appears around it. Gravity is in truth a very weak force. You defeat the gravity of the entire Earth every time you lift a spoon. To make a black hole, nature has to cheat, has to pile matter up so ferociously that even light gives up trying to climb away. And the center? The place we are really after tonight? The place where our whole question lives? In the mathematics, the center is a single point. Not a small ball. Not a dense little pit. A point, a place with no size at all, where, if you believe the equations all the way down, every scrap of the matter that fell in has been crushed to a density beyond density, and the fabric of space itself has been bent infinitely hard. We call it the singularity, and that word singularity is really just a physicist's polite way of admitting that the equations have started screaming, that they are handing us infinities, and infinities are nature's way of telling you that you have taken your theory somewhere it was never meant to go. So already, before we have gathered a single real clue, we have two suspicious characters in this story. There is the horizon, where your friend seems to freeze forever, and there is the center, this point of infinite crushing where our best theory throws up its hands. And the thing that connects them, the thing we are chasing, is time. What happens to time as you fall from the one to the other? What happens to time at the exact center? That is the case, and I promise you the answer is stranger and, in a certain way, calmer than anything you are expecting. Now I could just tell you the answer. I could give it to you in one sentence and we could all go to sleep early. But that would be a crime, because the joy of this, the real pleasure, is in the hunt. So I want to do it the honest way. I want to gather the clues the way the physicists actually gathered them, follow the false leads the way they actually got fooled, and arrive at the truth only when we have earned it. And I warn you now, we are going to be fooled at least once, badly, by that frozen friend at the horizon. It is the reddest of red herrings. But we will not throw it out. We will keep it, because even a wrong clue, understood properly, points you toward the right one. And to do all of this, I first want to introduce you to the man who lit the match. Because the equations we are about to lean on so heavily, the ones that predict the freezing and the falling and the crushing point at the center, those did not come from a comfortable university office with a fire in the grate. They came out of the mud. They came from a middle-aged man doing arithmetic by candlelight in a military dugout with artillery shells falling around him on the freezing Russian front of the First World War. He had a few months left to live, though he did not know it, and he spent some of those precious months walking, as he put it in a letter, in the land of another man's ideas. That other man was Einstein, and what Schwarzschild found on that walk was the first exact description of a black hole, decades before anyone believed such a monstrous thing could really exist. So let me take you to that trench, and to that letter, and to the quiet, doomed, brilliant man who wrote it. His name was Karl Schwarzschild, and by the time the war came for him, he was already a man of some reputation. He was not a boy dreaming in a classroom. He was the director of a great observatory, a man who had spent his life measuring the light of stars, weighing the heavens with patience and arithmetic. He was in his 40s. He had a wife, he had children, he had a warm study somewhere far behind the lines. And when his country went to war, he did a thing that seems almost unbelievable to me now. He volunteered. A middle-aged professor of astronomy, one of the finest calculating minds in Europe, put on a uniform and went to serve as an artillery officer, computing the trajectories of shells, working out with the same mathematics he had used on the stars where a falling weight of iron would come down out of the sky. Picture the strangeness of that for a moment. Here is a man whose whole life has been devoted to understanding gravity in the gentle, patient way. The slow curve of a planet, the fall of light across a lens. And now gravity has become his weapon. He is using the arc of a falling body to kill. I do not say this to judge him. I say it because I want you to feel the peculiar weather of that time, the way the deepest and the most terrible uses of the same idea were pressed together in one man's cold hands. And it was cold. The Russian front in the winter of 1915 was a place of frozen mud and long dark nights and the constant grinding fear of the guns. Somewhere in the middle of all that, in whatever quiet he could steal, Shortshold got hold of Einstein's brand new theory of gravity. Now you have to understand how fresh this was. Einstein had only finished his field equations, the real equations, the ones we still use, in November of that same year. November 1915. The ink was barely dry. Einstein himself had not found a clean, exact solution to his own equations. He had wrestled them into approximate answers, close enough to check against the wobble of the planet Mercury, but he did not have the exact thing. He thought, I believe, that finding an exact solution might take years, if it could be done at all. And then, a few weeks later, a letter arrives from the Eastern Front, from a soldier. And in that letter is the exact solution. Complete, clean, perfect. Einstein, I am told, was astonished. He wrote back that he had not expected anyone to find the answer in such a simple form, and certainly not so soon, and certainly not from a dugout within earshot of the Russian artillery. He thought enough of it to carry it himself before the Prussian Academy in Berlin in January of 1916 and present it to the assembled scientists as the work of Carl Schwarzschild, who could not be there because he was at the war. Let me read you the flavor of what Schwarzschild wrote, because it has stayed with me for a long time. He said that the war had treated him kindly enough, despite the heavy gunfire, to let him get away from it all and take, as he put it, this walk in the land of your ideas. This walk in the land of your ideas. Think about that sentence. Around him, the ugliest thing human beings had yet built, the machinery of mass killing roaring in the dark, and inside his head, a place of perfect quiet, a landscape made entirely of Einstein's geometry, where he could walk alone and unafraid. He found a door out of the trench, and the door led into the pure structure of space and time. And on that walk he discovered something no human being had ever seen before. He found the shape of the space around a perfect, round, heavy ball of matter, and buried in that shape, though he may not have fully grasped the beast he had caught, was the mathematics of the black hole. Here is the part that presses on my chest whenever I tell the story. That walk cost him everything. While he was stationed in the cold and the filth of the Russian front, he came down with a disease called pemphigus. It is a cruel autoimmune thing, a disorder in which the body turns against its own skin, raising blisters, breaking down the very surface that holds a person together. There was no real treatment for it then, nothing that could stop it. He grew sicker and sicker in that place, and by March of 1916 he was so ill that they sent him home, invalided out of the army, back to Germany. And there, in the town of Göttingen, on the 11th of May, 1916, Carl Schwarzschild died. He was 42 years old. Count the months for me. He sends the letter in December of 1915. His paper is read to the Academy in January of 1916. He is dead by May. Something like 4 months. 4 months between giving the world the first exact description of a black hole and leaving the world entirely. He never saw what became of his idea. He never knew that his name would be spoken more than a century later by people staring at photographs of these objects out in the sky. He never knew the word black hole, which would not be coined for another 50 years and more. He simply did the work in the worst place on earth and handed it to us, and then he was gone. And I want you to sit with a small, sharp irony, because I think it teaches something about how discovery really happens. Almost nobody, including Schwarzschild, including Einstein, thought that the strangest feature of that solution described anything real. There is a particular radius in Schwarzschild's answer, a certain distance from the center, where the mathematics does something violent and peculiar. The equations seem to blow up. quantities go to infinity. For decades, the finest physicists alive looked at that spot and shrugged. They called it a mathematical curiosity, a place where the coordinates misbehave, like the way every line of longitude piles up and crosses at the North Pole, not because there is anything wrong with the North Pole, but because our way of drawing the map falls apart there. They assumed it was a flaw in the description, not a feature of the world. They assumed no real star could ever be squeezed small enough to expose that radius to the open sky. Surely, they thought, nature would never be so crude as to actually build one of these things. They were wrong. That radius is the event horizon. It is as real as the floor you are lying on. And the reason they missed it, the reason it took 40 and 50 years for people to take it seriously, is the very thing this whole talk is circling around. They were confused about time. They kept looking at the black hole through the eyes of the distant watcher, the friend standing at a safe distance, and through those eyes, as we have already begun to see, everything freezes at that radius and nothing ever seems to cross it. So they thought of it as a wall, a barrier, a place where things pile up and stop. It looked from outside like the edge of the world, but that, as I keep muttering to myself and to you, cannot be the whole story. Because a wall where everything stops forever is a very strange kind of wall. Nothing actually touches it. Nothing rests against it. Things only ever approach it, slower and slower, dimmer and dimmer, fading toward it across an eternity that the falling person never experiences. And if you find yourself describing a place that everyone is always approaching and nobody ever reaches, you should get suspicious. You should feel the same itch a detective feels when every witness tells the same tidy story a little too smoothly. Somebody is leaving something out. The freeze is too clean. Nature does not usually hand you an infinity and mean it literally. When the mathematics starts shouting the word forever, it is very often not telling you about the world. It is telling you about the map. It is telling you that you have chosen a bad set of coordinates, a bad way of keeping time, and that the trouble is in your bookkeeping and not in the thing itself. So let us do what Schwarzschild could not do from his dugout, and what those early skeptics failed to do for half a century. Let us stop trusting the watcher's eyes. Let us climb down off the safe hillside and go stand in our imagination right beside the person who is falling. Because their watch is ticking, their heart is beating. Their story does not freeze. And when we finally listen to what their clock has to say, instead of what the distant telescope reports, the whole frozen picture is going to crack straight down the middle. And something far stranger, far more beautiful, and far more final is going to come pouring out. To do that honestly, though, we first have to be very careful about what a clock even is, and what we really mean when we say that time, near one of these objects, slows down. Because that phrase, time slows down, is one of the most abused sentences in all of physics, and if we are going to solve this case, we cannot afford to be sloppy about it. So let us settle that, first thing, before we go anywhere near the falling person's watch. What is a clock? A clock is not a magical little box with the letter time printed on the side. A clock is any physical process that repeats. A pendulum swinging. A crystal of quartz shivering back and forth when you run a little current through it. A heart squeezing and letting go. The sloshing of a child on a swing. A tuning fork ringing after you strike it. Every one of those is a clock, because every one of those does the same thing over and over, and you can count the overs. That is all counting time really is. You are counting how many times some faithful little process has repeated itself. Now hold on to that, because it changes what the phrase time slows down is even allowed to mean. When I tell you that time slows down near a heavy object, I am not telling you that some cosmic river got lazy. I am telling you something much humbler and much stranger at the same time. I am telling you that if you took two identical processes, two of the exact same clock, built in the same shop on the same afternoon, and you left one up here on the hillside and carried the other one down close to the heavy thing, then when you brought them back together and laid them side by side and counted, the two counts would not agree. The one that went down deep would have ticked fewer times. Not because it was broken, not because it was cold or tired or badly made. It ticked fewer times because fewer ticks actually happened for it. Less time, genuinely, physically unfolded along its path through the world. That is a hard thing to swallow, so let me slow it down even further, because we have all night and there is no reason to hurry. Suppose you and I each have one of those quartz clocks, and they are perfect, and side by side on this table they agree to better than one tick in a lifetime. I hand you yours, and you climb down toward the heavy object, and you sit there for a while reading a book, and then you climb back up. You did not feel anything happen to your clock. You watched it the whole way. It never stuttered. It never lurched. It ticked, from your point of view, as steadily and boringly as it ever had. You would swear on anything you liked that 1 second, for you, was one honest second the entire trip. And you would be right. That is the part people miss. Nothing local ever goes wrong. Your clock is fine. Your heart is fine. Your thoughts run at their usual pace. You have no way, sitting there, to feel that anything is unusual at all. And yet when you climb back up and we compare, yours is behind. Both of us are honest. Both of us watched carefully. Both of us are simply reporting what our own faithful little repeating presses actually did. The disagreement is not a mistake anybody made. The disagreement is the truth. There is no master clock hanging in the sky against which yours ran slow. There is only your clock and my clock, and the plain fact that the amount of time along your route through the world was less than the amount of time along mine. Time is not a single thing ticking everywhere at once. Time is something you accumulate, like miles on a road, and different roads through the neighborhood of a heavy object simply have different amounts of it. That last picture is the one I want you to carry with you, because it is going to save us later. Think of time the way you think of distance on a trip. If you and I drive from one town to another, me straight down the highway, you looping around by the coast, and we compare the odometers when we arrive, nobody is shocked that your odometer reads more miles. You took a longer road. You did not experience anything weird while you drove. Every mile felt like a mile. It is only in the comparison at the end that the difference shows up. Time near a heavy object works astonishingly like that. The heavy thing bends the roads. And clocks, all clocks, every repeating process there is, are just odometers for time, faithfully counting off however much of it their particular road happened to contain. So when the old textbooks say time slows down near a black hole, what they ought to say, if they wanted to be careful, is this. The closer a clock sits to the heavy object, the less time it racks up compared to a clock kept far away. And the effect is not a little rounding error. Far from the object it is tiny, the kind of thing you would need fantastically delicate instruments to notice at all. But as you bring the clock closer and closer to that critical shell we have been calling the horizon, the mismatch grows and grows. Gently at first, then steeply, then without any limit at all. A clock lowered slowly toward the horizon, and held there, and compared to ours up on the hill, ticks slower and slower against ours, without bound, running down toward a standstill that it never from our vantage quite reaches. And now, having said all that carefully, watch how it puts the frozen faller in a completely different light. Go back to your friend, the one we left hovering, dimming, reddening at the edge of the thing, the one you will never see cross. All this time we have been describing what you see. We have been standing on the hillside with a telescope, reading the light that struggles back up to us, and reporting that the image never crosses, never fades entirely, hangs there redder and dimmer and slower forever. But look at what we just learned. Everything we said about the frozen image was a statement about our clock, our road, our count of ticks up here where it is safe. It was never a statement about the faller's clock at all. We committed the very sin I warned about a moment ago. We took the reading on our own odometer and mistook it for the mileage on theirs. That is the crack in the case. That is the loose thread that, when you pull it, the whole frozen tapestry begins to come undone. Because the faller has an odometer too. The faller has a wristwatch, and a heartbeat, and a train of thoughts, and every one of those is a repeating process. A clock, honestly counting off the time along the faller's own road. And nothing we have said, not one word of it, tells us that the faller's clock does anything strange as the horizon approaches. We only know that the light coming back to us gets stretched and delayed without limit. Whether the faller's own quiet little watch stutters, or freezes, or sails right on ticking as calmly as it did on the launch pad, is a completely separate question, and we have not answered it. We have not even properly asked it yet. Feel how that reframes everything. The frieze we have been staring at for the whole first stretch of this investigation might be nothing more than a trick of perspective. It might be to the faller's real experience exactly what a friend shrinking into the distance is to that friend's real height. When someone walks away from you down a long straight road, they get smaller and smaller in your eye, and if the road were endless, they would dwindle toward a dot that never quite vanishes. But you do not for 1 second believe that they are actually shrinking. You do not think that the walking is squeezing them down toward the size of an ant. You know perfectly well that they are the same size they always were, striding along at their normal height, and that the dwindling lives entirely in the geometry between you and them, in the way the light folds up as the distance grows. The shrinking is real as an appearance and false as a fact about the person. What if the frieze is the same kind of thing? What if the faller, ticking and breathing and thinking, is sailing toward that horizon at a perfectly ordinary pace by their own honest reckoning, and the frieze we see is only the light folding up, only our road and theirs pulling so far out of step that the messages take longer and longer and longer to climb back up to us, redder and fainter each time, until the last photon that will ever reach us is on its way, and after that, silence. Not a frozen friend, a departed one. Gone across, on time by their own watch, while we up here are left holding an image that only looks like it stopped. I am not going to let myself declare that yet, mind you. A good investigator does not fall in love with the first pretty theory that walks in the door, and we have real work to do to earn this one. We have to actually get down into the mathematics of the faller's road and see what their odometer says. We have to ask whether the horizon is a wall or a doorway. We have to ask the sharpest question of all, the one this whole night is built around, which is not what happens at the horizon, but what happens at the very center. At that point, we keep calling r equals 0, where the equations start doing things that would make Shortshould himself put down his pencil. But we have found our thread. We have caught the distant watcher confusing his own clock for everyone's, and the moment you see that mistake clearly, you cannot unsee it, and the frozen picture will never again look quite so final. So let us do it properly. Let us climb in imagination into the falling frame, strap the wristwatch on tight, and fall. Not fast, not in a panic, but slowly and attentively, the way you would ease into cold water, watching that faithful little second hand the entire way down, and asking at each moment one simple question. Is it still ticking? Is it still ticking? And if it is, then how much of it, how many honest seconds of the faller's own true time, are left between the horizon and whatever waits at the center? So here we go. We are the faller now. Let the friend keep her safe distance and her patient telescope. She can have the frozen picture, the reddening smear, the long slow lie of it. We are inside the falling frame, and the first thing to report, the very first, is how ordinary it feels. That is the part nobody warns you about. There is no wall. There is no membrane you press through with a pop. The horizon is not a surface you can touch or scrape your knuckles on. It is a place where, if you shone a flashlight straight up, the light would still, just barely, climb away from you. 1 inch closer in, and the same flashlight beam, aimed with all your care at the stars, would curve back down like a thrown stone. But you, drifting across that boundary, feel nothing mark the passage. No jolt, no chill. The wristwatch ticks. 1 second. Another second. Exactly as it always has. That is the thing I want you to sit with. The place the whole outside universe swears is the edge of the world. The place where they believe you froze and hung forever like a fly in amber, that place slides past your elbow without so much as a whisper. If you had your eyes closed at the moment of crossing, you could not tell me afterward when it happened. There is no local test, no experiment you could run in a sealed room that announces, now, this is the horizon, now you have crossed. Einstein taught us that a long time before Shortshould ever picked up his pencil in the trenches. Falling freely, you feel no gravity at all. You are weightless. You float. The coffee, if you had brought coffee, hangs in its cup in a perfect trembling ball. And the horizon obeys that same gentle law. It is a one-way door you walk through in the dark, never feeling the hinge. Now, if it is so quiet, so smooth, so free of drama, why do I keep insisting something enormous has changed? Because it has, and the wristwatch is going to tell us if we are patient and keep our eyes on it. Let us not rush to the answer. Let us gather the small, strange facts first, the way you would notice, one by one, that a familiar room has been rearranged while you slept. Fact the first. You cannot turn around. Or you can fire your rockets. You brought rockets, let us say the best rockets ever built. Engines that could push you away from a whole burning sun. Point them down toward the center and light them and burn every drop of fuel you carry. And here is the thing that should raise the hair on your arms. It does not help. It does not slow your fall to the center by a single instant. In fact, and this is the part that turns the stomach the first time you truly understand it, the harder you fight, the sooner you arrive. Struggling costs you time. The soul who crosses the horizon and then relaxes completely, who does nothing, who simply floats and breathes and lets the fall take him, that is the one who lives the longest. The one who thrashes and burns and screams against it, the one who does everything a living creature is built to do when death approaches, that one dies first. Nature has flipped every instinct you own. Now why? Why would pushing away from a place bring you to it faster? On the outside, in the ordinary world, if you do not want to reach a wall, you walk the other way, and it works. Walking away from a thing increases the distance to it. That is what walking away means. It is the plainest fact of childhood, learnt before words. But inside the horizon, the center is not a thing you can walk away from, because the center is no longer sitting off in some direction. And that is the clue. Hold it. We are not ready to open it yet. But notice how heavy it is in the hand. Fact the second. Look up. When you fell in, the black hole was below you, a great round pit of darkness, and the sky was above, a shrinking bright circle of stars. That is what falling into a hole should look like. But cross the horizon, and something quietly rearranges. The darkness is no longer only below. Look up now, look at the stars, look in any direction you please, up, sideways, behind you, and every path your eye can follow, every single one, leads inward. The center is not under your feet. The center is in front of your face, and also behind your head, and also to your left and your right, all at once. There is no direction you can point that does not point, in the end, toward r equals 0. You are surrounded by a destination. You are enclosed by a single point. Try to say that sentence out loud and you will hear how it fights itself, and that fighting is the sound of ordinary language breaking against something ordinary language was never built to hold. Fact the third, and this one is the gentlest and the most terrible. The center is coming. Not you toward it toward you. It approaches the way tomorrow approaches. You are lying in your bunk on a slow night, you cannot sleep, and you know that morning is coming, and there is no lever in the room, no rope to pull, no clever trick of engineering that will keep the morning from arriving. You can feel the hours, you can read, you can pace, you can hold your breath, but the clock hand sweeps and the morning comes, because that is simply what the future does. It arrives. It is the one appointment nobody has ever missed. And inside the horizon, reaching the center has become exactly that kind of appointment. Not a place on a map you might steer around. A moment on your own timeline you are already sliding toward as helplessly and as calmly as you slide toward next Tuesday. I am getting ahead of the evidence. Forgive me. It is hard, once you have seen the shape of the answer, to lay the clues down one at a time with a straight face. Let me pull back and be a good detective again and simply keep watching that watch, because here is what the watch is doing while all this strangeness gathers around us. It is ticking, steadily, honestly, the same as it ticked in the kitchen back home. Tick. 1 second of real, lived, felt time. Tick. Another. Your heart is beating in your chest at its usual pace, your thoughts are running at their usual speed. Nothing about your own experience is stretched or frozen or slowed. That whole business of infinite time dilation, the eternal freezing the friend saw through her telescope, is nowhere to be found in here. It was always her illusion, painted on her side of the glass. On your side, time is just time, flowing the way water flows, and the question this whole long night is built around, is how much of it there is. How many honest ticks between the horizon you have already, silently, crossed, and the center that is coming for you like the dawn. And the answer, when we work it out, is going to be shockingly small. Not eternity, not a lifetime, not even an afternoon. For a black hole the weight of our sun, the entire remaining span of your existence, from the horizon to whatever waits at the middle, is measured not in years or hours or even in whole seconds. It is measured in millionths of a second. A time so brief that light itself, the fastest thing in all creation, barely has time to cross a small town before it is over. We are going to time that fall precisely, with a stopwatch that could survive the trip if any stopwatch could. And then we are going to build a bigger black hole, a monster the weight of millions of suns, and time the fall again, and find something that seems, at first, like a reprieve. But before any of that, before we put a single number to it, I want to understand why the number should be small at all. And to do that, we have to look, at last, straight at the clue I told you to keep holding. The one about why you cannot turn around. The one about why the center is a when and not a where. Take a slow breath. The watch is still ticking. It is still ticking. Let us follow it down. Think about a stone dropped into a well. You let it go, and it falls, and the reason it falls is nothing mysterious. There is a down, and the stone goes there, and no amount of wishing sends it back up the shaft into your hand. Now, near the surface of the earth, you could always cheat. You could reach in and grab it. You could put a shelf halfway down. You could fire a little rocket on the stone and hold it steady in the air. Down is only a preference here, a strong suggestion the earth makes, and a suggestion can be refused if you push hard enough. Hold that thought gently. Somewhere past the horizon of a black hole, down stops being a suggestion and becomes something else. Something with no shelf you can build and no rocket strong enough. And when I show you what it becomes, you will finally understand why the fall to the center is not only certain, but quick. But I am getting ahead of the evidence. Let me stay honest and slow, and let me earn that idea rather than announce it. So here is the puzzle sitting right in front of us. A person crosses the horizon. Their own watch keeps ticking, calm and ordinary, and I have promised you that watch reaches the center in a flicker, in millionths of a second, for a black hole the weight of our sun. Why so fast? You might guess it is because they are moving fantastically quickly, and there is truth in that, they are. But speed alone is not the heart of it. The heart of it is that the distance they have to cover is small, and the road they are on is a one-way street with no exits, no rest stops, no way to slow the crawl toward the end. Let me put the smallness in your hands first, because it surprises almost everyone. For a black hole, with the mass of the sun, the horizon sits at a radius of a little under 3,000 meters. Under 3 kilometers. That is the whole outer boundary, the edge of the thing, and inside that boundary there is only more inward to go down to the center. So the entire journey from the horizon to the very middle is a trip of less than 3 kilometers of radius. Think of that. You could walk it in half an hour on a flat road on an idle afternoon, and yet a falling body covers it not in half an hour, but in a sliver of time so thin that light, which crosses a room before you can blink, which laps the earth 7.5 times while you say one long sentence, has barely enough time to run from one end of a small town to the other before the whole plunge is finished. That is the skull we are dealing with. Small in distance, smaller still in time. Now let me actually put the number to it, the way I promised, with the imaginary stopwatch that could somehow survive. There is a clean result here, and it is one of the tidy little gems of this whole subject, because you would expect the answer to be a horrible tangle of an equation, and instead it comes out simple and almost pretty. If you take a body that falls straight in, drop from rest with just barely enough gentleness that it arrives at the horizon with nothing to spare, then the longest proper time it can possibly rack up on its own watch, from the horizon down to the center, is the horizon radius multiplied by pi and then divided by 2. That is the whole recipe, in the natural units where we measure time and distance in the same currency. Pi over 2 times the radius of the horizon. Nothing else. No mass buried in a logarithm, no ugly correction. Just that. Let me unwrap what that means for our sun-weight black hole. The horizon radius is that under 3 kilometers we just talked about. Multiply by pi, which is a little more than 3, and divide by 2, and then translate from a length back into an honest span of time by dividing by the speed of light, because that is what turns a distance in these units into seconds. When the dust settles, you get something in the neighborhood of 15 millionths of a second. 15 microseconds. That is the maximum. That is the most patient, most drawn out, most leisurely version of the fall available to anyone, and it is over before a housefly could beat its wings a single time. There is no strategy, no clever trajectory, no firing of engines that buys you more than that handful of microseconds. You may buy less. You cannot buy more. And I want you to sit with how strange that phrasing is, because it is the first crack of light coming through the door we are walking toward. The most time you can experience is a fixed, finite, tiny number set by the size of the hole and nothing about you at all. Notice what I just said, and notice what I did not say. I did not say the fastest you can fall. I said the most time you can experience. Those are ordinarily different questions. Out here, in the ordinary world, if I tell you the road is 3 kilometers long, the time it takes depends entirely on how you travel it. Sprint, and it is a few minutes. Stroll, and it is an hour. Sit down on the shoulder and refuse to move, and it is forever. The time to cover a stretch of ground is a thing you have some say over, because you can always choose to go slower, even to stop. That freedom, that ability to dawdle, is so basic to how we live that we never think of it as a freedom at all. It is just obviously true. You can always slow down. You can always stop and wait. Inside the horizon, you cannot. And that, when it finally lands on you, is the most disorienting fact in this entire subject. More disorienting than any infinity. Because it takes something you were certain of, something you have relied on every second of your life, and quietly removes it. The reason the fall to the center takes a definite, bounded, tiny amount of time is that stopping is no longer one of the things the universe offers you. Slowing your descent to buy more seconds is not merely difficult past the horizon. It is not merely beyond your engineering. It is the same kind of impossible as refusing to grow older. And I do not mean that as a poem. I mean it as close to literal machinery, and in a little while I am going to show you the gears of it, why the inward direction has quietly changed its nature into something you have no more power over than you have over the arrival of tomorrow. But I promised to earn that, so let me keep gathering the evidence rather than spend the payoff early. Here is a piece of the evidence, and it is a puzzling one, the kind of thing that ought to make you tilt your head. That simple recipe, pi over 2 times the radius, has a curious feature hidden in it. The bigger the black hole, the bigger its horizon radius, and so the bigger the answer. The fall lasts longer for a larger hole. That runs against a certain instinct, does it not? You might think a more massive black hole with its more ferocious gravity would snatch you to the center faster, would be more violent, more hurried. It is the opposite. A more massive hole is a gentler, slower, more spacious plunge, because the center is simply farther from the door. For our sun-weight hole, the fall is those 15 microseconds. But nature builds black holes far, far heavier than the sun. Holes weighing millions of suns, sitting quietly at the hearts of galaxies, and for one of those the horizon is not 3 kilometers across, but millions of kilometers across, and the fall from the edge to the center stretches from millionths of a second into whole seconds. Seconds. Long enough to have a thought, long enough almost to be afraid. So the picture is starting to turn inside out on us, and I love when a subject does this, because it means we were looking at it wrong and the right way is more interesting. We began with the frozen faller, the friend who from the outside seems to hang at the horizon forever, redshifting into darkness, never crossing, an eternity of not quite arriving. And now, from the faller's own point of view, we find not eternity but the very opposite, a fall so brief it is measured in flecks of a second, a whole inward universe crossed before a nerve could carry the signal of pain. 2 watches, the same event, and one reads forever while the other reads almost nothing at all. Both are right. That is not a trick, and it is not a paradox to be embarrassed about. It is the plain content of the theory, and holding both truths at once, gently, without forcing one to win, is exactly the frame of mind we need for what comes next. Because a natural greedy question is now sitting up and asking to be heard, and it is this. If the giant hole gives you whole seconds instead of microseconds, could you not use those seconds? Could you not, in that longer fall, do something, steer, resist, turn the ship around, at least try? The recipe says no. It says pi over 2 times the radius is the most time available and not a moment more. For the giant just as for the small one, only scaled up. It says those seconds are just as unstoppable as the microseconds were, that having more of the one-way road does not give you an off-ramp, only a longer stretch of the same inevitability. And I think that stubborn inevitability, surviving even when we make the hole enormous and the fall long and calm, is the loudest clue we have yet uncovered. Whatever forbids you from stopping is not about being crushed, not about speed, not about violence. It is something deeper in the shape of the place. So let us do the honest thing. Let us go and see whether you would even survive that fall long enough to test the question, whether the giant is truly as gentle as the arithmetic hints, before we open up the machinery of why the road runs one way. The watch is still ticking. Follow it down. Here is the strange thing about being torn apart. You would imagine that a bigger, more monstrous black hole is the more dangerous one to fall into. More mass, more gravity, more menace. That is the natural guess, and it is exactly backwards. Let me show you why gently, because this reversal is one of the prettiest little surprises in the whole business, and it hides inside a very simple idea. What actually kills you near a black hole is not the pull. It is the difference in the pull. Think of standing in a river. If the whole river drifts you along at the same speed, you feel nothing. You could be asleep on your raft. It is only when your feet are caught in a fast current and your head is in a slow one that you get stretched, twisted, pulled 2 ways at once. Gravity does the same thing to a falling body. Your feet, being a little closer to the center, are tugged a little harder than your head. That small disagreement, that gradient, is the thing that stretches you out like warm taffy. The physicists gave it a wonderfully undignified name. They call it spaghettification. And I love that word, because it tells you exactly what happens. You do not get crushed into a ball. You get drawn out into a long, thin strand, thinner and thinner, as the disagreement between your feet and your head grows without mercy. So the real question is not how strong the gravity is at the horizon. The question is how quickly it changes from your feet to your head. And here the arithmetic does something delightful. When you work out how steep that change is right at the horizon of a black hole, it does not grow as the hole gets bigger. It shrinks. The stretching you feel at the edge of a black hole falls off as the square of its mass. Double the mass, and the tearing force at the horizon drops to a quarter. Make the hole 1,000,000 times heavier, and the stretch at its horizon becomes 1,000,000,000 times gentler. The giant is the safe one. The little one is the butcher. Let me make that concrete, because numbers turn a claim into a picture. Take a black hole of just a few times the mass of the sun, one of those collapsed stars scattered through the galaxy. Its horizon is only a few kilometers across, and the change in pull across the length of your body, long before you ever reach that horizon, becomes ferocious. You would be stretched and snapped, drawn into a thread of your former self, while the horizon was still far below you. You would never arrive at the edge intact. You would be spaghetti in the approach, undone by the sheer steepness of the field, killed by the gradient and not by the depth. Now go the other way. Go to the giant at the heart of our own galaxy, the one with a mass of 4,000,000 and some suns. Its horizon is not a few kilometers. It is something like 12,000,000 kilometers across, a horizon you could fit a fair chunk of a solar system inside. And across that vast, lazy curve, the change in gravity from your feet to your head, right at the horizon, is mild. It is comparable to the difference you already feel standing on the Earth, where your feet are a smidgen closer to the planet's center than your head, and you never once notice. You could, in principle, drift across the horizon of that giant and feel almost nothing at all. No stretching, no warning, no fanfare, the most important boundary in the universe, and you would sail through it as calmly as passing from one room into another in the dark, not knowing the door had closed behind you. Sit with that for a moment, because it overturns the whole mood of the thing. We picture the horizon as a wall, a place of violence, a line where the screaming starts. And for a small hole it very nearly is. But for a big enough one, the horizon is a place where absolutely nothing local happens to you. Your watch keeps its steady tick. Your body stays whole. You could hold your hand in front of your face and see it perfectly well. There is no bump in the road, no flash, no threshold your instruments could point to and say, "There, that was it. That was the crossing." Whatever forbids your return has already taken hold silently and left no mark on you at all. And this is precisely what makes the whole mystery deepen rather than resolve. Because if the horizon can be so gentle, so unremarkable, so free of any local violence, then the inevitability we keep bumping into cannot be coming from any force you could feel. The small hole tears you apart with a force. You could measure that force, fight it, be destroyed by it. But the gentleness of the giant strips all of that away and leaves the inevitability standing there naked, with no muscle behind it. You cross a place where nothing happens, and yet from that instant your return is as impossible as unremembering tomorrow. The thing that traps you is not pushing on you. It is not pulling harder on your feet than your head. It is doing nothing to your body at all. And still it has you. So we have quietly ruled out a suspect. The freeze the outside friend sees is an illusion of viewpoint. We found that already. Now we find that the trap itself is not made of force. It is not the crushing, not the stretching, not the speed. A brave enough traveler, riding a big enough black hole, could reach the horizon in perfect comfort with a working watch and a clear head, ready to do physics, ready to report what they find, and the trap would still be sprung. Whatever holds them is written into the geometry of the place and not into the strength of its grip. That tells us where to look next. If the danger at the center is not simply that the pull becomes enormous, we had better ask what does become enormous there. What is it that genuinely runs away to something monstrous as you approach the very middle, the point we have been calling r equals 0, because something does. The gentleness of the giant's horizon is real, but it is not the whole road. It is only the doorway. Past the doorway, deeper in, closer to the center, the character of the place changes, and it changes in a way that no amount of being a supermassive gentle giant can soften. Here is the quantity we ought to follow. Forget the pull for a minute, forget even the gradient of the pull, the stretching. Ask instead about the curvature of space-time itself, the amount by which the geometry is bent, warped, folded away from the flat and ordinary space you and I move through every day. There is a way of measuring that bending with a single honest number, a number that does not care which coordinates you happen to be using, a number that cannot be fooled by a clever choice of viewpoint the way the frozen faller fooled us. Physicists build it out of the full curvature of space-time, squared up and summed so that nothing can hide, and they gave it a name after the man who wrote it down. They call it the Kretschmann Scala. You do not need the machinery, you only need to know what it is for. It is a truth teller. It reports how genuinely, unremovably bent the geometry is at any spot, and no change of perspective can torque it up or torque it down. At the horizon of our gentle giant, that truth teller reports a modest value. The geometry is bent, yes, but smoothly, mildly, nothing your body would object to. That is why the crossing feels like nothing. But now let the watch keep ticking. Let the traveler drift on inward, toward the center, and watch what that honest number does. It climbs. As you halve your distance to the middle, it does not merely double. It leaps up by a factor of 64, because it grows as the sixth power of how close you are. Halve the distance again, 64 times larger again. Again and again. The bending of space-time does not approach some large but finite ceiling as you near the center. It runs away. It heads for infinity, and it does so faster and faster the closer you get, with no floor beneath it and no wall to stop it. And this, unlike the frozen faller, unlike the mild horizon, is not an artifact. It is not a trick of coordinates. We chose the truth teller precisely because it cannot be a trick. Change your viewpoint however you like, and it still blows up. This is a real feature of the geometry, a place where the fabric is not merely stretched but torn, where the curvature is not large but literally without bound. The center of a black hole, this point we keep circling, is not a place where gravity is very strong. It is a place where the very shape of space and time comes apart at the seams, where the honest measure of bending has no finite value to report at all. So the gentle giant lured us in with a soft doorway, and now, following the same steady watch inward, we have found the thing that was hiding all along, waiting past the comfort of the horizon. Not a force, a wound in the geometry itself. And the moment we admit that the curvature genuinely runs to infinity, we are forced into a much harder and much stranger question, one that will finally crack the case open. Because if the geometry tears, then what exactly has happened to the space you were moving through and to the time on your ticking watch? Keep following it down. The watch has not stopped, and what it measures is about to change its very nature. So let us do the thing that good detectives do when the obvious story falls apart. Let us go back to the scene of the crime and look again, very slowly, at what actually happens when you cross that soft doorway. And I want you to hold on to your watch, because your watch is the one honest witness we have left. Everyone outside lied to us, or rather, they told us a truth that was only true for them. The frozen image, the fading red glow, that was a story about light and distance, not a story about you. You, falling, felt nothing special at the doorway. So what did change, if not your watch, if not your body, if not the ground under your feet? What changed was the meaning of the word forward. Let me try to say this carefully, because it is the strangest thing I know, and I have spent a long time being fooled by it. Out here, where you and I are sitting, there is a difference between space and time that feels absolute. You can turn around, you can walk to the left, then walk back to the right and stand exactly where you started. Space forgives you. You can revisit a place. But time does not forgive you like that. You cannot walk back to yesterday. You cannot stroll over to last Tuesday and shake your own hand. Time has a direction built into it, an arrow, a one-way street, and every one of us is carried down that street whether we like it or not. You are moving into the future right now at the steady pace of 1 second per second, and there is not a single thing you can do to stop it or turn it around. That, more than clocks or calendars, is what time really is. It is the direction you cannot refuse. Now hold those two ideas in your hands. Space, the thing you can move through freely, back and forth. Time, the thing that carries you one way and never lets go. Out here they are completely different in character. And the whole trick, the whole secret of the center of a black hole is that once you fall through that horizon, they trade places. I mean that almost literally. In the arithmetic that Schwarzschild handed to Einstein, there is a symbol for the radial direction, the distance from the center, and there is a symbol for time. And when you follow those symbols across the horizon and look at their signs, the thing that behaved like a direction in space, the in and out, the near and farther, starts behaving like time. And the thing that behaved like time out here starts behaving like an ordinary direction in space. The radial direction becomes the one-way street. Time, in a sense, becomes something you can lean into sideways. Sit with what that does to you. Out here, if I tell you there is a fire pit in the middle of the room, you simply do not walk toward it. You keep your distance. You circle it. You choose. The center of the room is a place, and places can be avoided by the plain act of not going there. But inside the horizon, the center is no longer a place in that sense. The center, the point we have been calling r equals 0, has stopped being a where and become a when. Reaching it is not like arriving at a spot on the floor. It is like arriving at tomorrow. And you already know, in your bones, how impossible it is to refuse tomorrow. This is why nothing escapes. Not because the pull is too strong. Strength has nothing to do with it. You could fire the mightiest rocket ever built. You could burn every ounce of fuel in the universe, point yourself straight back the way you came, and open the throttle all the way, and it would help you exactly as much as firing a rocket helps you avoid next Thursday. You are not fighting a force. You are trying to travel backward in time, and the geometry simply does not have that road. Every direction you can point, every way you can turn, every trajectory your rockets can carve, all of them, without exception, lead to smaller r. They lead inward. The way we out here have only a future and no way back to the past, you inside have only the center and no way back to the horizon. The singularity is in your future the way tomorrow is in mine. It is not ahead of you in space. It is ahead of you in time. And here is the quiet horror and the quiet beauty of it together. Nothing feels wrong. That is the part people never expect. You do not slam into a wall. You do not feel yourself being dragged. If the hole is big enough and gentle enough, you drift there in perfect calm, watching, breathing, wondering, and the whole time your future has narrowed to a single unavoidable moment. And you cannot even feel the walls closing because the walls are made of time itself, and you never notice time closing in. You only ever notice it in hindsight, and inside a black hole there is no one left to give the hindsight to. Let me put it another way, because I want this to land softly and completely. Imagine you are floating down a wide, slow river on a raft at night, and the water is so smooth you cannot tell you are moving at all. The stars overhead do not seem to shift. Your raft does not rock. By every local test you can perform, dipping your hand in the water, watching the ripples, you might swear you were sitting still on a pond. But far downstream, hidden in the dark, the river ends in a fall. And no stroke of the paddle in any direction can make the water carry you anywhere but down. That is what it is to fall past the horizon. The river is time. The current is your own future. And the paddle, your rockets, your struggling, your will to live, they can turn your little raft to face any way you please, but they cannot make the river run uphill. Now, a careful person, and I hope you are a careful person, because I have been trying to raise you into one for the last couple of hours. A careful person stops me right here and says, "Wait, you told me the outside watcher sees the falling friend freeze at the doorway forever. And now you tell me the falling friend sails right through and reaches the center in a snap of proper time. Both of those cannot be true. Somebody is lying. Nobody is lying. And this is the moment the whole case turns, so let me be slow and gentle about it. The two stories do not contradict each other, because they are not stories about the same thing. They are stories about two different times, kept by two different witnesses, and the deep lesson of all of this, the thing Einstein spent his life teaching us, is that there is no single master clock hanging in the sky that says what time it really is everywhere at once. There is your time, the honest ticking you carry with you, your proper time, and it is complete. It answers every question about your own life. And there is the time an outsider assigns to distant events by watching light crawl back to them across bent space. Those are different bookkeeping systems. The outsider's system simply runs out of numbers before your crossing ever gets entered into their ledger. It is not that your crossing does not happen. It is that their particular way of stamping dates on faraway events has a horizon of its own, a place past which it cannot reach, and your crossing falls forever just beyond the last page of their book. So the freeze was never a fact about you. It was a fact about the light you sent back, and about the way an outsider is forced to keep time. To you there is no freeze, no wall, no drama at the doorway at all. You cross, and then the direction called inward quietly becomes the direction called forward, and the center becomes your tomorrow, and your good honest watch keeps ticking the whole way down, measuring not distance anymore, but the last of your future. The watch did not stop. It never stops. It just started counting down something it had never counted before. And how much does it have to count? That is a fair and human question, and it has a startlingly precise answer, one you can almost hold in your hand. Because the fall from the doorway to the center is not endless. It is not even long. The geometry hands us an exact little sum for the most time you could possibly stretch that fall to last, and when we do the arithmetic for a hole the weight of our own sun, the answer comes out to something you could measure with a stopwatch faster than you could blink. So before we go chasing the deeper mystery of what waits at the very bottom, let us stop and time the fall itself. Let us find out in plain honest seconds exactly how long you would have. Here is how the geometry hands us the answer. There is a little quantity that measures the most time a falling person could ever squeeze out of the trip from the doorway to the center. In the natural units that relativity likes to use, it is just the number pi divided by 2 multiplied by the size of the hole. And by the size of the hole, I mean that same Schwarzschild radius we met earlier, the width of the doorway itself. Pi divided by 2 is about 1.5, a little more, 1.57 and change. So the longest possible fall, measured on your own wristwatch, is about 1.5 times the radius of the hole, once you translate that radius into a duration by dividing by the speed of light. That is the whole recipe. Take the width of the door, ask how long light would take to cross a stretch like that, and multiply by roughly 1.5. That is your budget of future. Now do the sum for a black hole with the mass of our own sun. We already said its doorway sits at about 3 kilometers across, a hair under 3,000 meters. Light crosses 3,000 meters in about 100,000th of a second, give or take. Multiply by that factor of 1.5, and you land on something close to 15 millionths of a second. 15 microseconds. That is the answer. From the moment you cross the horizon of a black hole, the weight of the sun, to the moment you arrive at the center, the most future you could possibly have, no matter how you twist and fire rockets and struggle, is 15 millionths of a second on your own watch. Sit with that number, because it is a strange and quiet little thing. It is faster than a housefly can beat its wings even once. It is faster than the sound of a snapping finger travels from your hand to your ear. In the time it takes you to think the word wait, you would already have crossed the whole interior of that black hole and reached the place where the equations give out. And here is the part that catches people sideways. You cannot make it longer by struggling. In ordinary life, if you are falling, you can slow yourself. You spread your arms, you open a parachute, you grab a branch. The falling takes longer. Inside this doorway, that instinct betrays you completely. If you fire your rockets, if you fight the fall, if you strain upward with everything you have, you do not buy yourself more time. You spend it faster. The struggling shortens the trip. The longest, gentlest, most patient possible fall, the one that wrings out every last drop of that 15 microseconds, is the one where you do absolutely nothing. You go limp. You let the geometry carry you like a leaf on a slow current, and even then, 15 millionths of a second is all the future the center will grant you. Why should fighting cost you time when out here fighting buys you time? Think about what the fall really is now. It is no longer a drop through space. It is a passage through time. From your present toward a moment fixed in your future, the way tonight leads to tomorrow. Out here, when you resist gravity, you are pushing against a direction in space. And space is forgiving. Space lets you dawdle. In there, the center is a moment, not a place. And resisting it is like trying to reach next week slowly by running very hard in a circle. All your effort, all that violent motion only churns up your own clock and burns your future faster. Stillness is the long road, motion is the short one. That is upside down from everything your body knows, and yet it falls right out of the arithmetic without any argument. Let me change the mass and watch the number change with it, because that tells us something too. Suppose the hole is not 1 sun, but 10. Then the doorway is 10 times wider, and your budget of future is 10 times longer. 100 suns, 100 times longer. The rule is beautifully simple. The time you have scales straight up with the mass. Double the black hole, double your last few moments. It is one of those rare places in physics where a thing you care about grows in the plainest possible proportion. No squares, no square roots, just a straight and honest line. Heavier hole, longer fall. And that little proportion is about to lead us somewhere genuinely surprising, so hold on to it. Because now let us stop being modest with our masses. Let us go to the middle of our own galaxy, the Milky Way, to the thing that lives there. Astronomers have weighed it with exquisite care by watching stars whip around it in great tight orbits over the years, and it comes out at about 4 million times the mass of the Sun. 4.3 million suns, near enough, packed into a single dark object we call, in the dry cataloging habit of astronomers, Sagittarius A star. 4 million suns. Take our little scaling rule and turn the crank. If one sun gives you 15 microseconds, 4 million suns give you 4 million times as much. And 4 million times 15 millionths of a second is no longer microseconds at all. It climbs up out of the realm of the housefly's wing beat and into the realm of ordinary human seconds. Tens of seconds. Something like half a minute of honest countable time from the doorway to the center of the giant at the heart of our galaxy. Half a minute. Think about how that transforms the whole scene. Around a black hole the mass of the sun, your visit to the interior is over before your nervous system could even register that it began. But around Sagittarius A star, you would have time. Time to breathe. Time to look around. Time to have a thought, a whole leisurely thought, and then another, and perhaps to notice with your own eyes whatever there is to be noticed on the way down. The doorway of that thing is not 3 kilometers across. It is something like 12 million kilometers across, wider than the orbit of the innermost planets around the sun. It is a vast, calm, dark threshold, and once you had crossed it, you would have the better part of a minute of future left to spend. The bigger the monster, the gentler and longer its swallowing. That is a sentence that ought to feel wrong, and it is exactly right. And it raises the obvious human question, the one you have probably been quietly holding this whole time, waiting for me to be honest about it. Fine, you say. So around a giant hole I would have half a minute. But would I be alive to spend it? Would there be a me at all to hold the stopwatch, or would I have been destroyed long before, torn to ribbons somewhere out near the door? It is the right question, and the answer is the strangest turn yet in this whole investigation, because it runs precisely opposite to what your fear expects. You would guess that the bigger and more monstrous the black hole, the more surely it would tear you apart. And the truth is the exact reverse. The little ones are the killers. The giants are the gentle ones. To see why, we have to talk about the difference between how hard gravity pulls on your head and how hard it pulls on your feet. And that difference has a name, and it is going to explain why a person could sail whole and breathing across the threshold of Sagittarius A star, while the very same person would be drawn out into a long thin thread of themselves before ever reaching the door of a small one. So let us follow that clue next, and find out who exactly would survive long enough to read the watch. Picture yourself standing upright, feet on the floor, head in the air, the ordinary way you stand while waiting for a kettle to boil. Gravity is pulling on every part of you. It pulls on your head, it pulls on your feet, it pulls on your belt buckle, and here on the earth, it pulls on all of them by very nearly the same amount, because your head and your feet are almost exactly the same distance from the center of the planet. Almost. Your feet are a little closer by the height of a person, and so gravity tugs your feet the tiniest bit harder than it tugs your head. The difference is so small you have never once felt it in your life. But it is there. It is real. And that little difference, the difference between the pull at your feet and the pull at your head, is the whole secret of who lives and who dies at the edge of a black hole. We have a name for that difference. We call it the tidal force, and the name is not an accident. It is the very same effect that lifts the oceans of the earth twice a day. The moon pulls harder on the water on the near side of the earth than it pulls on the solid body of the planet, and harder on the planet than on the water on the far side, and so the whole ocean gets stretched out gently into a long egg shape, and we call the two bulges the tides. Nobody is torn apart by the tides. The stretching is featherlight, but it is exactly the same kind of stretching. The pull on the near part being stronger than the pull on the far part, and if you make it strong enough, it stops being gentle. So here is the thing to hold on to. What tears you apart falling into a black hole is not the strength of gravity. It is the change in the strength of gravity across the length of your body. It is how much more your feet are pulled than your head, if you go in feet first. Near a black hole, your feet are closer to the center than your head, and if the pull grows steeply enough over those few feet of you, then your feet are yanked downward much harder than your head, and you are stretched and stretched and stretched, drawn out into a long thin thread. Physicists gave this the only name it could possibly have. They called it spaghettification. It is a joke, and it is also exactly correct. Now here is where the investigation takes its surprising turn, and I want you to follow the logic slowly, because it is beautiful and it is not what anybody guesses the first time. You would think a bigger black hole means a steeper, crueler stretch, more mass, more danger. And it is precisely the other way around. The tidal stretch you feel right at the horizon does not grow as the black hole grows. It shrinks. The more monstrous the black hole, the gentler the crossing. Let me show you why, and I will not use a single frightening piece of arithmetic to do it. The horizon of a black hole sits farther out the more massive the hole is. A little black hole has its horizon crammed in tight, right up close to all that mass, just a few kilometers out. A giant one, a hole of millions of suns, has its horizon flung out enormously far, millions of kilometers from the center. And the tidal stretch, that difference in pull across your body, depends terribly steeply on how close you are to the center. Close in, the pull changes viciously over even a short distance. Far out, the pull changes very slowly, very smoothly, almost not at all across the small length of a person. So the giant black hole does a curious thing. It hides its center so far away behind a horizon flung out to such a colossal radius that by the time you reach that horizon, you are still enormously far from where the trouble is. The pull on your feet and the pull on your head are nearly the same. You cross the threshold and feel nothing tearing at you at all. If you worked out the numbers for a hole like the one at the heart of our galaxy, or the far bigger one in the galaxy we call M87, the tidal stretch at the horizon comes out comparable to, or even gentler than, the difference in the Earth's pull between your head and your feet as you stand in your kitchen right now. You would drift across the most famous boundary in the universe, and your body would not so much as notice. The clue we found earlier, the watch that keeps ticking, the seconds counting calmly down toward the center, could actually be read. There would be a living person there to read it. The little black hole is another story entirely, and a grim one. Its horizon is jammed in close to the mass, only a few kilometers out from the center, and down there the pull changes so ferociously from one end of you to the other that you are stretched to a thread long before you ever arrive at the horizon at all. You would be spaghettified out in the open, well above the door, while a distant friend was still watching your frozen, dimming image hang at the threshold. For the small holes, the ones born from single collapsing stars, the death comes first and the horizon comes second. You never get to run the experiment from the inside. You are already undone. Say it plainly, because it overturns the natural fear so completely. The dangerous black holes are the small ones. The safe ones, the ones you could sail into whole and breathing, pocket watch ticking, are the giants. The bigger the mustard, the softer its embrace at the door. And so the person who actually gets to fall inward and find out what time does at the center, the person who lives long enough to be our detective on the inside, is the one who chose an enormous hole. Keep that person in mind. Keep them alive and intact and falling, watch in hand, because we are about to follow them past the threshold, and now that we know they survived the crossing, we can finally ask what the crossing does to them. Here is the first thing we should do once we are through. We should look at the fabric itself, not at the person, not at the watch, but at the shape of space-time, the curvature, the bending that gravity really is. Because gravity, in the picture Einstein gave us, is not a force reaching out and grabbing you like a hand. It is the curving of space and of time, and things fall simply because they follow the straightest possible path through a curved landscape. The way a marble set rolling on a warped sheet swings inward not because anything pulls it sideways, but because the sheet beneath it is bent. So the honest question about the center is not how hard does it pull. The honest question is how bent is the landscape, and what happens to that bending as you go down toward the very middle. And we can measure the bending. There is a number, a single honest number you can compute at any point in a curved spacetime that tells you how sharply the geometry is warped there, in a way that does not depend on how you are holding your head or which direction you happen to be looking. It is a way of squeezing the whole tangled shape of the curvature down into one quantity you can watch rise and fall. Out in empty space, far from any mass, that number is zero. The landscape is flat. Near the sun it is small, but not zero. At the horizon of a black hole, and this will matter enormously in a moment, that number is perfectly finite. Perfectly ordinary, nothing dramatic at all. The horizon, for all its fame, is not a place where the geometry does anything violent. That is our whole reason for believing a person could cross it and feel nothing. The curvature there is mild. But start falling inward from the horizon and watch that number. It begins to climb. Slowly at first, then faster still, and the closer you get to the center, the more savagely it rises. It does not rise like a hill. It rises like a cliff going straight up to the sky. And when you ask the mathematics what that number becomes exactly at the center, at the point we have been calling the middle all this time, the point where the radius has shrunk all the way down to nothing, the answer it hands you is not a big number. It is not a huge number. It is infinity. The curvature does not merely get large at the center. It runs off the top of every scale there is. It diverges. It blows up without limit. And that word infinity is where this whole investigation is quietly going to turn again. Because in physics, infinity is almost never an answer. It is almost always a confession. When your equations hand you infinity, they are not telling you that something in the world is truly, physically, endlessly large. More often, they are telling you that the equations themselves have reached the edge of what they know and have walked off it and are now falling. So we have found, down at the center, a place where the very theory that carried us all this way, Einstein's beautiful geometry that has been right about everything, opens its mouth to speak and produces only a shriek that rises forever. We should not take that shriek at face value. We should ask, very carefully, what it is really trying to tell us. But before we can ask that, there is something even stranger waiting for us just inside the horizon. Something about the direction we are falling in and about the difference between a place and a moment that changes the meaning of the word center altogether. So come with me across that edge now, gently, the way you would wade into a river where the bottom drops away without warning. From the outside, we have watched a friend seem to hang at the horizon forever, reddening, dimming, going quiet. But we have already learned not to trust that picture. It is a story the outside tells itself. The friend, on her own little raft of a wristwatch, feels nothing special at the boundary. She sails through, and once she is through, once she is inside, something happens to the world around her that is so peculiar I have to slow all the way down and lay it out one piece at a time, because if I say it too fast, you will nod and agree and not feel the ground move under you, and I want you to feel the ground move. Out here, where you and I are sitting, the world has a very ordinary arrangement. There are 3 directions you can go in space: left and right, forward and back, up and down. And in every one of those, you are free. You can go one way, then change your mind and go the other. If you walk east, nothing in the laws of nature forbids you from turning around and walking west. But there is one direction in which you have no such freedom at all, and that is time. You are marching into the future. You cannot stop. You cannot turn around and stroll back into last Thursday. You did not choose to move forward in time, and you cannot choose to stop. It simply carries you, second after second, whether you like it or not. That helplessness, that one-way current, is what makes time feel so different from space. In space, you are a free wanderer. In time, you are a leaf on a river. Now hold that difference in your mind, because here is the thing that happens when you cross the horizon of a black hole. The direction that pointed toward the center, the radial direction, the in and the out, the very direction you would ordinarily be free to reverse, stops behaving like a direction in space. It starts behaving like a direction in time. And the old time direction, the ticking that used to carry you helplessly forward, loosens its grip and starts behaving a little like a direction in space, something you have some freedom to move about in. They trade places, not as a figure of speech, not as a loose analogy to help the beginners. In the honest mathematics of Schwarzschild's solution, inside the horizon the radial coordinate becomes what we call time-like, and the time coordinate becomes space-like. The two swap their very natures. Let me try to make you feel what that means for the poor friend on her raft. Out here, if I told you you must reach the center of the earth, you would say, well, that is hard, but it is a matter of digging. It is a place. It sits at a particular spot, and if I am clever and stubborn enough, I can go toward it or away from it as I please. The center is aware, but once our friend is inside the horizon, the center of the black hole stops being aware. It becomes a when. Reaching the singularity is no longer like reaching a city at the end of a road, a city you might in principle steer around or turn back from. It becomes like reaching next Tuesday. Tell me, how do you avoid next Tuesday? You cannot walk around it. You cannot floor the accelerator and outrun it. You cannot decide you would rather stay in Monday a while longer. Tuesday is not a place in front of you. It is a moment ahead of you in time, and time only flows one way, and so Tuesday is coming for you no matter what you do, no matter how you thrash, no matter how powerful your rockets. That is exactly, precisely, mathematically the situation of anything that has fallen past the horizon. The center is in its future, and the future, as we all know down in our bones, is not optional. I want to sit with how strange and how oddly comforting this is at once. All the frantic images we carry around of a ship firing its engines against the pull, of straining against a current, of clawing back toward the light, all of that assumes the center is a place and the pull is a force you could, in principle, overpower with a big enough engine. But there is no force to overpower here. There is nothing to push against. Firing your rockets toward, as we would say, away from the center, does not slow your arrival. In some ways it hastens it, the way struggling in quicksand does you no favors. Because you are not being dragged across space toward a spot. You are simply being carried forward in time toward a moment, and every clock, every heartbeat, every thought you have is itself the very motion that brings that moment closer. To ask how to avoid the singularity, once you are inside, is to ask how to stop time from passing for yourself. And the answer to that is the same grim, simple answer it has always been everywhere in the universe for everyone. You cannot. This is why nothing comes back out. People sometimes think the escape is impossible because gravity is just so terribly strong in there, stronger than any rocket, stronger than light itself, a sort of tug of war that light happens to lose. That picture is not quite right, and now you can see why. It is not that the exit is guarded by an overwhelming force. It is that the exit is not in a direction you can travel anymore. Out is not a way you can go, for the same reason yesterday is not a way you can go. The geometry has tilted the very meaning of forward so far over that all roads, every single possible path, every direction a beam of light could be aimed, all of them lead down the throat of time toward that central moment. There are no paths that lead out. In the same way, there are no paths in your life that lead into the past. The center is not surrounded. The center is simply, unavoidably, later. And here is a small mercy hidden in the horror of it, or at least a strange dignity. Our friend, sailing on her raft, does not experience this as a wall or a trap slamming shut. She experiences it the way you and I experience the ordinary passing of an afternoon. Nothing grabs her. Nothing announces itself. If the black hole is large enough that the tides are gentle, and we spoke earlier of how the giant ones are gentle at the horizon, she might not even be able to tell from inside her cabin, by any local measurement, at what instant she crossed the point of no return. There is no sign on the boundary. There is no bump. The current simply, quietly, became inescapable, and she floats on, and the center of everything is now not somewhere out ahead in the dark, but somewhere out ahead in time, approaching at the steady, indifferent rate of 1 second per second. The same rate at which your own future approaches you right now, in your chair, wherever you are. So the word center, which we started with so innocently, has quietly rotted away in our hands and become something else. When you and I say the center of a room, we mean a spot, a place, a location you could mark with a piece of chalk and walk up to and stand on. But the center of a black hole is not a spot on any map you could draw of the inside. You could not fly a little flag there and say, "Here it is, come visit." It is not a here at all. It is a then. It is the last moment on the clock of anything that falls in, the final tick after which the clock has no more ticks to give. And that reframing, that turning of a place into a moment, is the true answer to the question we have been circling for all this time. The question of what happens to time at the very center. because now you can begin to see that asking what happens to time there is a little like asking what is north of the North Pole. The question sounds perfectly reasonable right up until you understand the geometry, and then it quietly dissolves. But I do not want to leave you thinking this is just a clever trick of words, a philosopher's game about wheres and whens. There is hard mathematics under every bit of it, and there was a long stretch of years when even the finest physicists were not sure whether this whole swapping business was something real in nature or just an artifact of Schwarzschild's particular way of drawing his coordinates. The way a flat map of the round Earth makes Greenland look monstrous. Maybe, some of them thought, the singularity was like that. A smear of ink where the mapmaker's projection broke down, and with a cleverer map it would smooth away to nothing. That was a serious worry, and a fair one, and settling it took one of the most beautiful pieces of reasoning in the whole subject, done by a man drawing little pictures of light cones and asking a question nobody had quite thought to ask before, about surfaces and about being trapped. His name was Roger Penrose, and the year was 1965, and the thing he did was so simple in its beginning that you could almost miss how much weight it would carry. He was not trying to solve the equations of a collapsing star all the way down. That was the trouble with the old approach, you see. People had been trying to write out the full motion of some idealized ball of dust, perfectly round, falling in on itself, and then they would look at what came out at the center and worry about whether the mess they found was real or just a consequence of assuming everything was perfectly round. Because nothing in nature is perfectly round. A real star is lumpy. It spins a little faster here, sags a little there, has a hot spot and a cold spot. And the suspicion, the entirely reasonable suspicion, was that all these singular horrors only showed up because of the unnatural neatness of the model. Let the star be lumpy and honest, the hope went, and the collapsing matter would miss itself the way a crowd rushing through a doorway mostly misses, and instead of piling to a point it would swirl and slosh and settle, and there would be no infinite anything. Penrose did not argue with that hope directly, he did something cleverer. He asked a question about light. Picture, if you would, a little sphere of light, an expanding flash like the surface of a soap bubble blown very fast, growing outward in every direction. In ordinary empty space, that outer surface gets bigger as time goes on. Of course it does. That is what expanding means. And the inner edge, the part of the flash heading inward toward the center, that part shrinks, its surface area gets smaller as you would expect. Outgoing grows, ingoing shrinks. That is the plain and sensible state of things everywhere you have ever lived. Now Penrose asked, what if you found a place where that stopped being true? What if you found a surface so deep in the grip of gravity that even the light trying to go outward, even the part of the flash racing away from the center as hard as light can race, found its surface area shrinking anyway? Not slowing, shrinking. The outgoing light pointed straight out, still losing ground, still being carried inward, because the space it is swimming through is itself pouring toward the center faster than the light can climb. A surface like that, where both the ingoing light and the outgoing light are forced to converge, where every direction that light can go is a direction of shrinking, Penrose called a trapped surface, and the name is exactly right. Light is the fastest messenger there is. If light itself cannot get out, cannot even hold its own ground, then nothing inside can. The region is sealed, not by a wall, but by the shape of the geometry itself. Here is the elegance of it, and I want you to sit with this a moment, because it is the whole trick. He did not have to assume the star was round. He did not have to assume anything about the lumps and the spin and the slosh. He only had to assume that somewhere in the collapse, just once, a single trapped surface managed to form. And you can show, without much fuss, that if you crush enough matter into a small enough region, a trapped surface must form, lumps or no lumps. The lumpiness does not save you. Once the matter is dense enough, the light is caught, and a trapped surface exists, and that is the only ingredient the argument needs. From that one seed, using the way that gravity always bends the paths of light and matter toward each other, never apart, always toward because gravity only pulls, Penrose showed that the paths of things inside that surface cannot go on forever. They come to an end. not a soft end, not a place where you drift out the far side into some other region. An end. The path of a falling particle traced forward simply stops after a finite amount of its own time with nowhere to continue to. The mathematicians have a cool phrase for this. They call it geodesic incompleteness. A geodesic is just the natural path of a freely falling thing, the straightest line available in a curved world, and incomplete means it does not go the distance, it runs out of track. And a path that runs out of track, that ends after a finite tick of a wristwatch with no possible continuation, that is what a singularity really is, stated honestly. Not necessarily a point of infinite density you could photograph. A place where the paths of things stop, where the future itself develops a raw edge. What made this land like a thunderclap among the people who understood it was that it needed so little. No special symmetry, no perfect sphere, no convenient assumption you could accuse of smuggling in the answer. Just matter gets dense enough, a trapped surface forms, and then given the mildest and most reasonable conditions on how energy behaves, that gravity pulls and not pushes, the singularity is unavoidable. It is not a fragile feature of an idealized toy that a more careful model would wash away. It is generic. It is what collapse does. The Greenland on the map turned out to be a real continent after all. Penrose had shown that the breakdown at the center was not the mapmaker's smudge. It was a true feature of the territory, forced there by logic, and for that piece of reasoning, among his other work, he was given a share of the Nobel Prize in Physics, though not until the year 2020, more than half a century after he drew those little pictures of light cones tipping over. And now I have to tell you the part that gives me a small shiver every time, because a good idea in physics is never content to stay in the one room where you built it. Penrose had made his argument about a star, about collapse, about matter falling in and getting trapped and running out of future. But there was a young man named Stephen Hawking who was thinking about time running the other direction, and he noticed something. If you take Penrose's reasoning and you turn it around, if you run the film of the universe backward instead of forward, the whole cosmos becomes a kind of collapse too. Everything we see is flying apart. The galaxies drifting away from one another, the whole thing expanding. So wind it back. Backward, everything rushes together. Backward, the universe is a contraction, denser and denser as you go into the past, the very picture of matter falling in on itself, only now it is all of matter, the whole sky doing the falling. So Hawking and Penrose sat down together, and in 1970 they published a paper with a plain, heavy title, On the Singularities of Gravitational Collapse and of the Cosmos, and in it they proved that the same kind of reasoning, the same trapped surfaces, the same running out of paths, applies not just to the death of a star, but to the birth of everything. Given the same reasonable conditions on energy, the universe's own past must contain a singularity, a place where the paths of things, traced backward, come to an edge and cannot be continued. We have a name for that edge. We call it the Big Bang. And what their theorem quietly told us is that the Big Bang is not merely a moment when things were hot and small. It is, in the eyes of general relativity, the same kind of creature as the center of a black hole, a place where the theory's own paths terminate, where the smooth fabric develops a boundary it cannot see past. Think about what that means for a second, gently, the way you might turn a smooth stone over in your hand in the dark. The thing we have been chasing, this strange center where time does something we cannot describe, is not some exotic monster hiding out in the far corners of space where only a doomed astronaut would ever meet it. It is the same as the thing at the bottom of our own beginning. Every particle in your body traces its lineage back to that edge. The singularity is not only in the future of the unlucky, it is in the past of us all. The same crack in the theory sits under the black hole and under the dawn of time, and it is, in a real mathematical sense, one crack seen from two sides. But I have been letting these two men hand us their conclusion a little too smoothly, and I do not want you to drift off thinking a theorem is a photograph. A theorem tells you that something must exist, that the paths must end. It does not, and this is important, it does not tell you what it is like there, what is actually happening in the last flickers before the paths run out. It is like a very rigorous letter informing you that a certain road definitely comes to a cliff. It does not describe the cliff. It does not tell you the shape of the last stretch of road, whether it is straight and calm or whether it thrashes about wildly in its final yards. And when a few very careful people finally worked out what that last stretch of road looks like, when they zoomed all the way in on the approach to the edge itself, expecting perhaps a smooth, quiet crush, they found instead something nobody had any right to expect, something that churns and tumbles and will not hold still. A chaos so peculiar that I am going to have to build it up for you slowly, piece by piece, before it will make any sense at all. So let me build it up the way it deserves. When you picture the collapse of a star down toward that final point, the natural thing to imagine is a kind of orderly squeezing. You imagine a ball of gas getting smaller and smaller, always a ball, always round, always the same, just tinier and tinier until it winks out. Smooth. Symmetrical, everything pressing inward evenly, like a fist closing gently around a marble. That is the picture almost everyone carries in their head, and it is a very reasonable picture, and it happens to be almost entirely wrong for a real lumpy, imperfect collapse. Because here is what a few very stubborn people found when they stopped assuming everything was perfectly round and let the geometry do whatever it wanted. As you approach that final point, the different directions of space stop cooperating. Think of it this way. Imagine you have a lump of dough, and you squeeze it. If you squeeze evenly, it just gets smaller. But real squeezing is never even. Push on a lump of dough, and it squishes flat in one direction while it squirts out sideways in another. It gets thinner top to bottom, while it stretches longer side to side. Now imagine that as soon as it stretches long in one direction, something switches, and suddenly that long direction starts collapsing while a different direction shoots out. And then that switches too. Stretch here, crush there, and then, a heartbeat later, crush here, stretch there, back and forth, over and over, faster and faster, and never ever settling into a pattern you could predict. That is roughly the flavor of what these people found waiting near the center. Space near that final point does not simply shrink. It shrinks in two directions while it stretches in the third, and then it swaps which directions are doing what, and then it swaps again, and the swapping never stops and never repeats itself in any tidy way. Each little chapter of Stretch and Crush, each one of these episodes, has been given a name, and the geometry marches through one, then another, an endless procession of them, each one different, each one handing off to the next in a manner that looks, for all the world, like pure chaos. And I want to be careful with that word chaos, because I do not mean simply messy or complicated. I mean chaos in the strict sense, the sense a weather forecaster fears. It means that if you started with two collapsing stars that were almost identical, differing by the tiniest imaginable whisker, and you let them both fall toward that final point, the sequence of stretching and crushing they went through would drift apart and then diverge wildly until the two histories had nothing recognizable in common at all. The tiniest difference at the start blows up into a totally different story by the end. That is the signature of genuine chaos. The same signature you find in a column of rising smoke that breaks into curls, or in the tumbling of a leaf falling from a tree, where you simply cannot say in advance which way it will flip next. Now there is a second strange thing tangled up in all this, and it is stranger than the churning, if you can believe that. As the geometry approaches the final point, the different places in space stop talking to each other. Let me try to say what I mean. In the ordinary world, if I jostle the air here, you feel the breeze over there a moment later. Things are connected. A disturbance in one spot travels to its neighbors, places are in touch. But as you fall toward that center, the connection between neighboring points of space gets choked off. Each little patch of space begins to evolve entirely on its own, doing its own private dance of stretch and crush, deaf and blind to what the patch right next to it is doing. It is as though a great crowded ballroom, everyone dancing together to one piece of music, slowly had the music fade out for each dancer separately, until every single person was dancing to a different tune in their own head, hearing nothing of their neighbor, each lost in a private and increasingly frantic rhythm. The whole notion of the geometry as one connected thing comes apart. It becomes a collection of lonely points, each thrashing by itself. Take a breath with that, because it is a lot. The picture of a smooth ball closing gently around a marble is gone. In its place, we have a storm where space stretches and crushes in an endless, never-repeating chaotic sequence, and where every point rides out that storm alone, cut off from every other point, right up until the paths run out. I should tell you plainly where this stands, because I try never to dress up a guess as a certainty. This churning, chaotic picture of the last moments is not a fully proven theorem the way the earlier result was, the one about the road ending at the cliff. This is a conjecture, a very well-supported and beautiful conjecture, worked out by a handful of physicists whose names are attached to those little chapters of stretch and crush. When people put the equations onto machines and let the numbers grind, when they simulate a lumpy, realistic collapse and watch what the geometry actually does as it plunges inward, they see exactly this churning, this oscillation, this decoupling of neighboring points. The numbers agree with the picture beautifully, but a full, airtight mathematical proof that this is always and everywhere what happens for every possible collapse that we do not yet have. So I hold it the way you should hold any strong idea that has not been nailed shut. I take it very seriously. I let it inform how I imagine the center, and I keep a small honest doubt tucked in my pocket, ready in case nature surprises us again the way she loves to. But suppose the churning picture is right. Suppose that really is what the last stretch of road looks like, a wild tumbling storm of stretching and crushing space, each point alone. Then I want you to notice something almost funny about it, something that turns the whole mood of the thing on its head. We started this evening with a picture of the center as a place of ultimate stillness, a point. The quietest, smallest, most final thing you could imagine. Everything crushed down to nothing, motionless, done. And now, having followed the clues all the way in, we arrive not at stillness, but at the most violent, most restless, most agitated behavior anywhere in all of physics. The center is not calm. The approach to the center is the least calm thing there is. It is a place where space itself cannot stop trembling. And here is where I have to be honest with you about something that has been quietly gnawing at the whole investigation from the very beginning. Something I have been circling and circling. Every single thing I have just described to you, the stretching, the crushing, the chaos, the lonely decoupled points, all of it comes out of one theory, one magnificent theory, the theory of curved space and time. The very theory that gave us the road and the cliff and the frozen faller and the swapping of space for time. And that theory, when you push it right up to the final point, does something no honest theory of nature should ever do. It gives you infinity. It tells you the curvature grows without any bound at all, larger than any number you could name, and then larger than that. It tells you the churning gets infinitely fast. It hands you an infinity, and it goes silent. Now, I have spent a long life around equations, and I will tell you a small secret about them. When an equation that is supposed to describe the real world hands you an infinity, it is almost never telling you that something in the world is truly infinite. It is far more often telling you that the equation itself has been pushed past the edge of where it knows what it is talking about. An infinity in your answer is very often the sound a theory makes when it breaks. It is the equation clearing its throat and admitting, if you listen closely, that you have wandered somewhere it was never built to describe. So when this beautiful theory of curved spacetime, which has passed every test we have ever thrown at it out here in the wide and gentle universe, suddenly starts screaming infinities at the center, I do not conclude that nature contains a true infinity crouched at the heart of every black hole. I conclude something humbler, and to me, far more exciting. I conclude that we have found the exact spot where our best theory stops being our best theory, where it runs out of road of its own, and where some deeper thing we do not yet possess has to take over. And that raises a question so simple a child could ask it, and so deep that no one on this earth can yet answer it fully. Is there really a point there at all, a true honest-to-goodness point, of no size whatsoever, holding all that mass? Or is the point itself just another illusion, like the frieze we started with, a thing the old theory insists upon, right up until a better theory gently taps it on the shoulder and says, no, no, it does not go like that down here. To even begin to chase that question, we have to leave the theory of gravity behind for a little while and go and knock on the door of the other great theory of this century, the strange and slippery physics of the very small, and ask it what it thinks of a particle squeezed down to nothing at all. So let us do that. Let us walk over to that other door and knock gently and see who answers. Behind it is the physics of the very small, the physics of atoms and electrons and light, and it has a temperament all its own. Where gravity is smooth and patient and loves a nice curved surface, this other physics is jittery and shy and refuses to sit still. And the very first thing it tells us, before we have even finished asking our question, is something you might find hard to swallow. It tells us that you cannot pin a thing down. Not perfectly, not ever. Not for love, not for money, not for all the careful engineering in the world. Here is the flavor of it. Take a little particle, an electron say, and try to trap it in a box. Make the box small. The particle rattles around inside. Now make the box smaller. And here is the odd part. The smaller you make the box, the faster and wilder the particle rattles. It is not that you are shaking it, you are only squeezing it. And nature answers your squeeze with a kind of fury. Squeeze harder, and it fights back harder. There is a certain size tied to the particle's own mass and to the speed of light, below which the very idea of saying here it is, right here, at this exact spot, stops making sense. Physicists have a name for that size. They call it the Compton wavelength. You do not need to remember the name, you only need to remember the spirit of the thing. Every particle carries around it a little haze of uncertainty, a fuzziness it will not surrender, and if you try to crush it down smaller than that haze, the particle simply refuses to be a point. It insists on being a smear. Now hold that thought right next to the thing we found at the center of the black hole. General relativity, the theory of the large and the smooth, marched us down to the middle and said, with perfect confidence, there is a point there. No size at all. Everything, all of it, all that mass, packed into a spot smaller than the tip of a needle, smaller than an atom, smaller than nothing. And now this other theory, the theory of the small, folds its arms and says, that is not how it goes down here. You cannot have a point. I forbid it. A point would mean a particle pinned to an exact location with no haze at all. And that I will never allow. So we have two of the finest theories human beings have ever built. Two theories that between them have passed every test we could throw at them, every single one, for the better part of a century. And they are standing in the same room, pointing at the same tiny place, and they are flatly contradicting each other. One says point, the other says impossible, and they cannot both be right. That is not a small disagreement. That is not a matter of getting the decimals to line up. That is two maps of the same territory, and where they overlap, one shows a mountain and the other shows the sea. When you find something like that in physics, you should not be discouraged. You should be delighted. Because a contradiction like that is a signpost. It is nature telling you, in the plainest language it knows, that right here, right at this spot, there is something you have not understood yet. Not something small, something big, something new. The place where two great theories collide and cannot both be true is exactly the place where the next great theory is hiding, waiting for somebody clever enough, or lucky enough, or stubborn enough to dig it out. And people are digging. I want to be honest with you about the state of it, because it would be easy to spin you a tale and pretend we have the answer neatly wrapped. We do not. What we have are attempts. Brave, imaginative, half-finished attempts to build a theory that speaks both languages at once, the language of the large and the language of the small, a theory of quantum gravity. And nobody yet has one they can be sure of, but some of the attempts are so pretty and so suggestive that they are worth sitting with for a while in the dark. Let me tell you about one of them, because it takes the very thing we started with, the freeze, and turns it into something wonderful. There is an idea worked out not so long ago by a fellow named Rovelli and a colleague of his named Vidotto, and they call the thing at the heart of it a Planck star. Here is the picture. As the star collapses inward and the matter squeezes down and down, general relativity wants it to keep going all the way to that forbidden point. But the quantum physics, the physics that will not be crushed, pushes back. And the closer you get to unthinkable density, a density so enormous it has its own special name, the Planck density, the harder that push becomes. Until, at some point, the push wins. The collapse stops. Not because anything solid got in the way, but because nature simply will not be squeezed any further. And then, having stopped, the thing does what a squeezed spring does. It bounces. Sit with that for a moment. A bounce. Not a point of infinite density sitting there forever, frozen and impossible. Instead, matter falling in, reaching the limit, refusing to go further, and springing back out. The black hole in this picture is not a bottomless pit at all. It is more like the bottom of a very deep breath, the moment where the inhale turns around and becomes the exhale. The collapse becomes an explosion. A black hole quietly turns itself, over unimaginable spans of time, into its mirror image, a thing that pours matter and light outward instead of swallowing it. A white hole. And now here is where the whole 3 hours we have spent together comes curling back on itself like a snake catching its own tail. Because I told you, way back at the beginning, that time does not run at one speed near these objects. I told you that to the faller, everything happens quickly, in a few ticks of a wristwatch, while to the distant friend, the very same events seem to drag out toward forever. Well, take that lesson and lay it over the bounce. In the Planck star picture, the bounce is fast. In the star's own reckoning, in its own proper time, the whole business, collapse, bottom, rebound, might take hardly any time at all. A flash. A blink. But to us, watching from far away, out here where our clocks run at their ordinary lazy pace, that same quick bounce gets stretched and stretched and stretched by the very time dilation we spent so long unraveling. Stretched so enormously that a bounce which takes an instant down there could take longer than the present age of the universe up here. Do you feel what that does to the freeze? The friend who seemed frozen at the horizon, the image that dimmed and reddened and hung there forever, might not be a trick of the light after all. Or not only that, it might be a genuine shadow of a genuine event that really is, from our point of view, taking almost forever, an event that is still unfolding, still in progress, that will not finish its slow story until time so long they make a human lifetime, make the lifetime of a star look like the flick of an eyelash. The thing we mistook for a dead man frozen in ice might be a living process caught in the amber of stretched time, waiting out a bounce we will not live to see complete. Now I have to slam on the brakes here and tell you plainly, because I promised I would. This is not established fact. This is not something anyone has measured. The Planck star is one idea, one guess, one hopeful sketch drawn by a few clever people, and there are other sketches drawn by other clever people that look quite different. Some say the information about everything that fell in gets smeared onto the horizon and slowly leaks back out. Some say the inside connects to somewhere else entirely. Some say things I would not even know how to picture for you. Nobody has caught nature in the act. We cannot see inside. The horizon is, by its own nature, a one-way door, and no letter has ever come back through it to tell us how the story ends. So when I hand you the Planck star, I hand it to you the way you would hand someone a beautiful shell you found on the beach, saying, "Look at this, isn't it something?" but not saying, "This is how the ocean works." What we can say, what we can stand on with both feet, is the shape of the mystery. We know the smooth theory says point. We know the jittery theory says no point is possible. We know the two of them meet at the center of a black hole and cannot agree, and that their disagreement is not sloppiness on our part, but a real crack running down the middle of everything we know. And we suspect, all of us, that whatever fills that crack, whatever the true theory turns out to say, it is going to be strange, and it is going to be beautiful, and it is going to change the way we think about the words we have been throwing around so casually all evening, the words here and there and now and then. So before we can even ask whether the center is a place or a moment, we have to face the possibility that it is neither, that both of those homely little words, place and moment, are tools we made for life up here on the surface of things. In the wide, gentle country where clocks tick evenly and rulers hold their length, and that we have carried them down into a region where they were never meant to go, like carrying a candle down into water and being surprised when it will not light. And yet we cannot just leave the candle sputtering there in the dark and walk away. When a good tool fails, the failing tells you something. Watch a carpenter whose level will not sit flat on a warped board. The bubble drifts and will not settle, and at first he is annoyed, but then he grows thoughtful, because the tool is honest, and it is telling him the board is not what he assumed. Our words here and now are behaving like that bubble. They will not settle, and the refusal to settle is itself the clue we have been chasing all night, the clue we were too polite to look at directly. So let me look at it directly. Down inside the horizon, we found that the radial direction, the direction that used to mean nearer or farther, had quietly turned into a direction in time. To go inward was no longer a choice, like walking toward a wall, but a certainty, like arriving at the day after today. That was already enough to make your skin prickle. But there is a second thing waiting just past it, and it is stranger, and softer, and harder to hold. It is the question of what the curvature itself is doing as you slide down that ramp of forced tomorrows toward the middle. Curvature is a word I have been using gently, so let me make it a little more solid without dragging in a page of symbols. Think of the crust on top of a custard as it sets, or the skin of the water in a pond. Flat means a marble laid on it stays put. Curved means the marble rolls, and the more sharply the surface bends, the faster the marble picks up speed, and the more two marbles set side by side will hurry toward each other or fly apart. Space-time has a bending like that, and near an ordinary star the bending is gentle. A long shallow valley you could roll a marble around for a lifetime. Near the horizon of a black hole the valley has grown into a steep bowl. And as you go inward toward the center, the bowl does not level out at the bottom the way a real bowl does. It gets steeper and steeper without stopping. Here is where I have to be careful and honest with you, because this is the exact spot where honesty matters most. When we write down how sharp the bending gets, using a particular measure of curvature that does not care which coordinates you chose, a genuine measure that every observer would agree on, we find that it grows like 1 divided by the radius raised to the 6th power. Now that phrase, 1 over radius to the 6th, is a mouthful, so let me tell you what it means in the body rather than the head. It means that as the radius shrinks toward nothing, the bending does not merely get large. It runs away. Halve the distance to the center and the bending leaps up by a factor of 64. Halve it again and it leaps by another 64. There is no floor. The bowl has no bottom. The marble rolls forever faster and there is no ground to catch it. And that, at last, is the thing people mean when they say the frightening word, singularity. It is not a solid object sitting at the middle like a cherry in the middle of a cake. It is not a tiny heavy pebble you could, in principle, reach out and touch. It is the name we give to the place, or the moment, where the bending of space-time, the very quantity our whole theory is built to track, marches off toward infinity and refuses to come back. And I want you to notice, drowsily, comfortably, that this is not the same kind of trouble we met at the horizon. At the horizon the numbers blew up too, you remember. The outside watcher saw the falling friend freeze and redden and never quite arrive. But that blow-up was a trick of the bookkeeping. Change how you keep time, ride along with the faller, and the horizon smooths out into nothing special. A line you cross without a bump, like passing from one county into the next on a dark road with no sign. The horizon singularity was a shadow cast by a bad choice of ruler. You could make it vanish. This one you cannot make vanish. No clever change of ruler, no shift of viewpoint, no cleverness of any kind straightens out a curvature that every possible observer measures as infinite. It is baked into the geometry itself, sewn into the fabric, and not into the pattern we drew on the fabric. That is why we call it a real singularity and not a coordinate singularity, and the difference between those two, which sounds like a dusty piece of jargon, is really the difference between a stain on your glasses and a hole in the world. Wipe your glasses and the first one is gone. The second one is still there when you look again. So we have a spot at the center where the geometry says the bending is infinite, and we have already learned that this spot is not somewhere ahead of the faller in space, but somewhere ahead in time, an appointment that cannot be missed. Put those two together, slowly, the way you would fit two pieces of a puzzle by feel in a dim room. What they say together is this: every path, every possible history of anything that falls past the horizon, every marble and mote and messenger runs forward in its own time for a little while, a short unhurried little while, and then simply stops. Not stops the way a car stops at a curb with more road beyond that it declines to travel. Stops the way a sentence stops when the page is torn off. The path reaches the center and there is no next moment. The clock does not read infinity. The clock reaches its last tick and there is no tick after it, because there is no after. The people who study these things have a phrase for that, and it is a lovely gray, careful phrase, the kind mathematicians use when they want to say something wild without waving their arms. They call it geodesic incompleteness. A geodesic is just the natural path a freely falling thing takes, the straightest line available in a curved world, the path a thrown stone would follow if you subtracted the ground. Incomplete means you can follow that path forward, tracking the faller's own honest wristwatch, and after only so many ticks, the path cannot be continued. It is not that the path leaves the universe through some door. There is no door and no leaving. The path just ends, and the theory that drew the path has no more to say. It hands you the pen and shrugs. Now a suspicious mind, and I hope by now yours is as suspicious as mine, will lean back and object. Surely, you say, this is an accident of the perfect roundness we assume. We built our black hole out of a single lonely mass, perfectly spherical, sitting perfectly still, no spin, no lumps, no personality. Real stars are none of those things. Real stars bulge and churn and turn. They are speckled and dented and blotched. They collapse crooked. Surely a real collapse, an honest messy one, would miss the exact center the way a poured stream of water almost never hits the precise middle of the drain. Surely the infinities are a fairy tale that only the perfect fairy tale sphere can tell. Surely the mess saves us. It is a wonderful objection. I made it myself, in my own head, and I suspect nearly everyone who has ever thought hard about this has made it, because it is the natural hope. Give nature a little untidiness, and the runaway curvature scatters harmlessly, the paths swerve past the bad point, and there is no true end to anything, only a very violent squeeze followed by, who knows, some kind of recovery. If that were so, the singularity would be a bookkeeping ghost after all, a thing that lives only in the pristine equations and dies the moment you let the real world be its usual lopsided self. For a long time, that hope was respectable. Nobody could prove it wrong, and nobody could prove it right, and so people held it the way you hold a coat you are not sure you will need, half on and half off. And then, in the middle of the 1960s, a young mathematician in England picked up a genuinely new tool, a way of thinking about these problems that owed less to grinding through the equations of the perfect sphere and more to the shape of things, to what topologists call the global structure, the way the whole cloth is stitched rather than the thread count in one corner. And with that tool he was able to ask the question the messy way, without assuming any roundness at all, without assuming stillness, without assuming anything but that gravity pulls, and that a certain very reasonable condition on energy holds. And the answer he found was not the comfortable one. The answer he found was that the mess does not save you, that once the collapse has gone far enough, once a certain kind of surface is formed, the end of the paths is sealed no matter how crooked and turning and speckled the star that made it. And to see how he did that, we have to talk about the strangest and most beautiful idea in this whole long night, a thing called a trapped surface, and about the man who dreamed it up while the rest of the field was still polishing its perfect spheres. Picture a flashlight, an ordinary flashlight, the kind you keep in a drawer for when the storm knocks the power out. You switch it on in the middle of a dark field, and the light rushes away from you in a growing sphere, a shell of brightness getting bigger and bigger every instant. That is the most ordinary thing in the world. Light spreads out. The front of it, the leading edge, is a sphere whose area is always increasing as it flies away from the bulb. Nothing surprising there. Now imagine you could stand somewhere so strange that when you switched on your flashlight and pointed it straight out, away from the center, away from everything, the light still went outward as fast as light can go, and yet the sphere it was drawing got smaller. Not bigger. Smaller. The area of that outgoing shell of light shrinking, even though every photon in it is racing outward at the full speed that nature allows. That is a trapped surface. That is Penrose's idea, stated plainly. A surface where even the light that is trying its hardest to escape, the outward going light, is nonetheless being carried inward, because the space it is traveling through is itself falling faster than the light can climb. The outward beams and the inward beams both converge. Both shells shrink. There is no direction you can shine a lamp where the wavefront grows. And the marvelous thing, the thing that made this more than a curiosity, is that Penrose realized you could define this condition locally. You could point at a region and check it, right there, with the geometry in your hand, without knowing anything about the whole rest of the universe, without assuming the star was a perfect ball, without assuming it sat still, without assuming it was empty around it. If a trapped surface exists, you have caught the thing in the act. And then the theorem does its quiet, ruthless work. Here is the logic. And I want to walk it slowly because it is a lovely piece of reasoning. Take that trapped surface. Follow the light going outward from it, forward in time. Because the surface is trapped, that light is converging, the beams are being focused, drawn together. Now there is a general fact about gravity, and it is the one physical assumption the whole argument leans on. Gravity, if the energy in a region is not doing anything perverse, if it is the ordinary, well-behaved kind of energy we actually find in stars and gas and dust, gravity always focuses light. It never defocuses it. A lens made of matter always converges the rays, never spreads them. So light that has already started converging, under gravity that can only make it converge harder, is a rush toward a meeting point. The beams must cross. And when the beams of a converging family of light rays are forced to cross, you reach what is called a focal point, a caustic, a place where the paths pile up and can go no further as the well-behaved boundaries they were. Put those two facts side by side. The trapped surface says every outgoing null ray is already converging. The energy condition says gravity can only tighten that convergence, never loosen it. And the geometry of the situation says the whole future of that trapped surface is boxed in, penned inside a region that cannot open back up to infinity, cannot spill out into the wide, roomy universe far away. The light has nowhere to go but into itself. And so the paths, the histories of things must simply stop. They run out. They come to an end after a finite amount of proper time, a finite tick of the wristwatch, and there is no continuing them, no smooth road onward. That stopping, that abrupt cliff edge where perfectly good paths simply cease, is what the mathematicians call geodesic incompleteness. And geodesic incompleteness is the honest, careful, grown-up definition of a singularity. Not infinite density, not a point of infinite anything. Just this. Paths that end and cannot be continued, and nobody can tell you what lies past their ending because there is no past their ending inside the theory at all. Do you feel how different this is from the old picture? The old worry was always, well, the singularity is at the exact center at r equals 0, and the center is a special place, and real stars are lumpy and spinning and off-kilter, so maybe the lumps miss each other, maybe the spin flings things sideways, maybe in a real messy collapse nothing ever actually arrives at that one privileged point. And Penrose's answer, delivered without a single assumption about symmetry, was that it does not matter. The singularity was never really about arriving at a special place. It was about the paths ending. And the trapped surface guarantees the paths end. You can spin the star, you can dent it, you can make it as irregular as a crumpled newspaper, and as long as the collapse gets far enough to wrap a trapped surface around itself, the ending is sealed. The mess does not save you. That was the whole point I promised you a moment ago, and now you can see it was earned, not asserted. And the man who found this, he was young, and he was thinking about the shapes of things, about how spaces can be connected and folded and stitched. The way a topologist thinks, rather than grinding through the coordinates the way most of the relativity people did in those days. The story he told later was that the idea came to him in a moment of ordinary life, crossing a street in the middle of a conversation. One of those flashes that arrive sideways when you have stopped straining for it and half forgotten the problem. He was crossing a road with a colleague, the talk paused for the traffic, and in that little gap of silence the notion of the trapped surface simply appeared to him, and by the time they reached the far curb the conversation had moved on and the idea had quietly filed itself away to be written down later. That was 1965. A short paper, a few pages, and it changed what the singularity meant, from an accident of perfect spheres into a theorem about the generic fate of anything that falls too far. Many years afterward, in the year 2020, that line of work was recognized with the Nobel Prize in Physics, and rightly so, because it was the first time anyone had proved, really proved, with the rigor of a theorem rather than the hope of an example, that these endings are not exotic. They are ordinary. They are what gravity does when you give it enough rope. Now I want you to hold on to the flavor of that argument, because it has a second use, and it is a use that made Penrose's tool suddenly enormous, far bigger than one dying star. Notice what the theorem actually needs. It needs a converging family of light rays. It needs gravity that focuses rather than defocuses, the well-behaved energy condition, and it needs the geometry to be trapped, the outgoing shells shrinking. Nothing in that recipe says the shrinking has to be a star. Nothing says the convergence has to point forward in time toward a black hole. And a certain young man in Cambridge, thinking hard about cosmology, sick a great deal of the time and thinking all the harder for it, looked at Penrose's argument and had the audacity to run it backward. To take the whole expanding universe, the entire sky of galaxies flying apart from one another, and to imagine playing the film in reverse, everything rushing back together, and to ask whether that reverse collapse would trap its own light the same way a dying star traps its own. If today the cosmos is expanding, then yesterday it was smaller, and the day before smaller still, and the light rays of the far past were converging as you follow them backward, converging just the way the outgoing rays of a collapsing star converge going forward. The same focusing theorem should bite. The same ending should be forced. And so the very same mathematics that seals the center of a black hole ought to seal the beginning of everything. The moment we have taken to calling the Big Bang. The instant where all the paths of all the matter in the universe run backward to a wall and simply stop being continuable. The end of the star and the beginning of the world, the same theorem, the same trapped light, the same finite proper time to the edge of the map. That was the road those two walked down together. And where it led is a thought I would like to set down gently and let you carry into the dark for a while, before we ask the harder question of whether the theory that proved all this even believes its own conclusion. So let us ask that harder question now quietly, the way you would poke at a loose floorboard to see whether the whole floor is sound. General relativity has just handed us a proof. It has told us, with all the force of theorem and logic, that inside a collapsing star the paths of matter must run out, must terminate after a finite little stretch of proper time, must arrive at a place where the curvature climbs past every bound. The theory has spoken. And here is the strange, almost comic thing. The moment the theory finishes speaking, it stops being able to say anything at all. It has proved its own silence. It has used its own rules to march you to a spot where its own rules no longer hold. That is a very unusual situation for a physical theory to put itself in, and I want you to sit with how odd it really is. Think about what an equation is. At bottom, it is a promise. It says, give me the situation now, and I will tell you the situation a moment later. Give me where the planet is and how fast it moves, and I will tell you where it goes tomorrow. That is what the equations of physics do for a living. They take a present and they hand you a future. Now, the equations of general relativity are a set of these promises about the shape of space-time itself, about how curvature here leads to curvature there. And as you follow the curvature inward toward that central point we keep circling, the numbers the equations produce do not settle. They grow. That measure of bending I mentioned before, the one that climbs like 1 over the radius to the 6th power, it does not approach some large but sensible value. It runs to infinity. And infinity, in a physical equation, is not an answer. It is the equation throwing up its hands. Let me be very plain about what that means. Because people hear the word infinity and they think it is describing something, some enormously dense nugget sitting at the middle. That is not what is happening. When your formula for the density of matter or for the curving of space hands you infinity, the formula is not reporting a fact about the world. It is confessing that it has left the region where it knows how to speak. It is like asking a map what lies past its own torn edge. The map does not have a wrong answer for you there. It has no answer. The paper simply ends. And the singularity at the center of a black hole is exactly that torn edge, drawn in the language of curvature instead of ink. Now I have spent a good part of my life being suspicious of infinities in physics, because I have seen them come and go. When I was working on the problem of how electrons and light talk to each other, the equations kept coughing up infinities too, and for a while it looked as though nature itself were misbehaving. It turned out nature was fine. It was our way of asking the question that was clumsy. We had to learn to handle the arithmetic more carefully, and when we did, the infinities folded away and left behind numbers that agreed with experiment to a staggering number of decimal places. So when I meet a fresh infinity sitting there at the center of a black hole, my first instinct is not awe. My first instinct is suspicion. I want to ask, is this infinity telling me about the world, or is it telling me about the limits of my pencil? And the honest answer, the answer nearly every physicist would give you if you caught them in a candid moment, is that it is telling us about the pencil. The infinity at r equal to 0 is almost certainly not a real feature of nature. It is a signpost. It is general relativity's own way of raising its hand and saying, past this point, do not trust me. I have carried you as far as I can go. Someone else must take over from here. A good theory, a really honest theory, knows the borders of its own kingdom. And general relativity, to its enormous credit, points straight at the one place where it must be incomplete. It does not hide the crack. It shines a light on it. Why should the theory break down precisely there and nowhere else? Because at the center, you are trying to do something the theory was never built to do. General relativity is a theory of smoothness. It imagines space-time as a beautiful continuous rubber sheet, curving gently, bending kindly, every point flowing into the next without a seam. That picture works gorgeously across the whole sweep of the cosmos, from the orbit of a moon to the swing of a galaxy. But at the center of a black hole, the theory asks that smooth sheet to fold into a crease of zero width and infinite sharpness. And a smooth thing cannot do that while staying smooth. It is like demanding that a calm, still pond contain a splash that is infinitely tall and infinitely thin at a single point. The water simply cannot hold that shape. Something else must happen, something the placid equations of the pond were never written to describe. And we already know the name of the something else, even if we do not yet know its face. It is the small world. It is the world of the quantum. Because here is a fact that ought to have been nagging at us this whole long night, and I have deliberately kept it in my pocket until now. The rules that govern the very small are not the smooth, well-mannered rules of general relativity. They are jumpy, grainy, uncertain rules. And down at the center of a black hole, everything is being squeezed toward the very small. You are taking the mass of an entire star and pressing it toward a point far tinier than an atom, far tinier than the nucleus of an atom, tinier than anything we have ever probed. At those sizes, the smooth theory and the grainy theory are both trying to describe the same patch of the world at the same time, and they do not get along. They have never gotten along. Reconciling them is the great unfinished business of physics, and the center of a black hole is the one arena where nature forces the two of them into the same room and locks the door. Let me give you just one taste of why the quantum rules refuse to allow a true point, one clue from the small world that we will pick up properly a little later. There is a rule down there, a deep one, that says you cannot pin a particle down to too small a region without paying a price. Try to trap a particle in a smaller and smaller box, and it fights you. It grows more and more uncertain in its motion, it jitters harder, it resists being confined. There is a smallest sensible region into which you can corner a given particle at all, set by its own nature, and if you try to squeeze it below that, the ordinary picture of a particle sitting at a place simply dissolves. Now the singularity asks you to take all the matter of a star and squeeze it not into a small box, but into no box at all, into a mathematical point of exactly zero size. The quantum rules look at that request and they laugh. They say, you cannot do that. It is not that it is hard. It is that the very idea of a thing being nowhere sized is a kind of nonsense in our language. And so the quantum world hands us a strong hint, long before we have a finished theory, that the true point at the center does not exist. Something intervenes, Something stops the squeeze. But I am getting ahead of the investigation, and I promised you I would move gently. Hold that hint. For now, let us just stand honestly at the border and admit where we are. We followed the falling observer past the horizon. We watched space and time trade their coats. We understood at last why the center is a moment and not a spot, why it waits in the future like an appointment no one can miss. We took the mathematics of Penrose and saw that this ending is not some accident of a perfectly round star, but a forced conclusion, a fate written into the geometry itself. And then we walked the same road backward and found it pointing at the birth of the whole universe. Everything hangs together. The logic is tight. And at the very end of that tight, beautiful chain of reasoning sits a link that is not there at all, a link the theory itself tells us it cannot forge. That is not a defeat. I want to be clear about that, because it would be easy to hear all this as a gloomy confession, physics failing, throwing up its hands in the dark. It is nothing of the kind. It is one of the most thrilling situations a scientist can find himself in. We have a theory good enough, rigorous enough, honest enough to lead us by the hand right up to the doorway of its own ignorance, and then to say, plainly, the room beyond this door is furnished with rules I do not know. That is not the sound of physics ending. That is the sound of physics pointing at the next thing to be discovered, and the next thing is enormous. Whatever governs the center of a black hole is the missing marriage of the very large and the very small, and the day we understand it will be one of the great days. And yet even that is not the end of the surprises waiting at the center. Because you might imagine that as you fall those last few instants toward r equal to 0, whatever is happening, at least it happens simply. You picture a smooth, steady, quiet crushing, the walls closing in with a kind of grim patience, everything narrowing calmly to the point. That is the natural picture. It is also, it turns out, very probably wrong. The last moments before the theory gives out are not calm at all. When people sat down and asked what the geometry actually does as it approaches that final wall, they did not find a smooth, quiet squeeze. They found something wild, something churning, something almost like a storm. And that storm has a name and a strange history, and it is where we turn next. The name is a small thicket of syllables, so let me just give you the three men behind it and be done. Belinsky, Kalatnikov, and Lifshitz. Three Russian physicists working in the 1960s and into the 70s who asked a very stubborn question. Forget the tidy pictures. Forget the perfect sphere. Forget the assumption that everything falling in is arranged as neatly as an orange. Take a real collapse, lumpy and crooked and off-center the way real things always are, and ask what the geometry does in the very last flicker of time before it reaches the wall. And what they argued, what has come to be called their conjecture, is one of the strangest results in all of this strange subject. They found that as you approach that final moment, the shape of space at each little spot does not settle down. It swings. It stretches one way and squeezes another, and then, without warning, it flips, and now it stretches the way it was squeezing, and squeezes the way it was stretching. And then it flips again. And again. And the flips do not slow down as you get closer. They speed up. They pile on top of each other faster and faster, an endless drumming of stretch and squeeze and flip crammed into a sliver of time that is running out. Think of a bead of dough between a baker's hands. He rolls it long and thin, then he turns it and presses it flat, then he rolls it the other way. Now imagine he cannot stop, and every roll comes quicker than the last, and there is no final shape the dough ever reaches, only more and more furious kneading squeezed into less and less time. That is the flavor of it. The old comfortable picture, the calm patient narrowing to a point, is gone. In its place is a churning, a boiling, a thing that will not hold still. And here is the part that I find almost eerie, the part that took me a while to make my peace with. As you get very close to the wall, the different spots in space stop talking to each other. Ordinarily, if you jiggle the geometry over here, the jiggle spreads to over there. Ripples travel. Neighbors feel each other. That is what it means for space to be connected, for it to be a single continuous fabric. But in this final churn, the churning gets so fast, so violent, so local, that each little patch begins to dance entirely on its own. Your patch of space is doing its wild sequence of stretch and squeeze. The patch a hair's breadth away is doing a completely different wild sequence, and they no longer influence one another at all. The fabric, in a sense, comes apart into a dust of independent little worlds, each one drumming out its own private storm, each one deaf to its neighbors. The continuous sheet of space-time you have trusted your whole life to be smooth and shared and single, right at the end, dissolves into a crowd of strangers who no longer speak. Now I want to be honest with you about the standing of this idea, because honesty is the whole game, and I will not dress up a guess as a certainty. This chaotic churning, this endless flipping, is a conjecture. It is not a theorem in the way that Penrose's result is a theorem. Nobody has proven it with full rigor for every case. What people have done is study it very carefully with pencil and paper for simplified situations, and later put it on machines, on computers, and let the equations grind forward toward the wall and watch what they do. And the machines over and over show the churning. They show the flips speeding up. They show the little patches coming loose from one another. So it is not idle speculation. It is a picture that keeps passing the tests we know how to give it, while stubbornly refusing to be nailed down with a proof. That in-between place, well supported and not yet settled, is a very common and very honest place for a physicist to stand, and I would rather stand there squarely than pretend I am somewhere I am not. But notice what the churning is really telling us. It is not telling us what happens at the center. It is telling us that the theory on its way to the center is working itself into a frenzy. The equations are not gliding gracefully toward an answer. They are thrashing. They are drumming faster and faster, generating structure on smaller and smaller scales, packing infinitely much, wiggling into a closing window of time. And whenever a theory starts behaving like that, whenever it starts producing endless detail at endless speed as you push it towards some edge, an experienced person begins to suspect that the theory is not describing the world anymore. It is describing its own nervous breakdown. The chaos near the wall is one more voice, joining the diverging curvature and the terminating paths, all of them saying the same thing in different tongues. This is where I stop being able to tell you the truth. This is where I have run out. So let us follow that suspicion. Let us take seriously the idea that the point, the actual point of infinite density at r equal to 0, is not a real thing that nature builds, but a mirage that our particular theory produces when we push it past its territory. And to test that suspicion, I want to leave gravity alone for a moment and go visit the other great pillar of what we know, the physics of the very small. Because the physics of the very small has a rule that bears directly on this, and it is a rule with real teeth. Here is the rule, in plain words. In the world of the very small, you cannot pin a thing down to a single spot. You just cannot. The more tightly you try to confine a particle, the more it resists, and it resists not by pushing back with a force you can measure, but by refusing to have a definite position at all. Squeeze it into a smaller and smaller box, and it becomes more and more frantic, more and more spread out in its motion, until the very idea of its sitting still at one place stops making any sense. Every particle carries with it a kind of minimum smear, a fuzziness below which you simply cannot corner it. This smear even has a name and a size, a length that belongs to each particle, and the rule is blunt. You cannot trap the thing in a region smaller than that length. Nature will not permit the pin to go all the way through. Sit with that for a moment against everything we have been building. The classical picture, the beautiful ruthless machinery of general relativity, insists that all the matter of a collapsed star gets driven to a single point, a place with no size whatsoever, zero width, zero breadth, a location smaller than anything. And the physics of the very small stands up and says, quietly but firmly, you cannot do that. You cannot put matter at a point. The particles will not be pinned. There is a flaw to how small a region a piece of matter can be confined within, and a point, a true point, is infinitely far below that flaw. So here we have our two greatest bodies of knowledge, both tested to exquisite precision, both trusted by every working physicist alive, and they flatly contradict each other about the center of a black hole. One demands a point, the other forbids it. They cannot both be right there. And that contradiction is not an embarrassment to be swept aside. It is a signpost. It is nature holding up a lantern over the exact spot where our understanding has a hole in it and saying, dig here. Which brings us, at last, to the suspects. The people who are trying to guess what actually fills that hole, what really happens when you drive matter down to densities so absurd that both of our theories throw up their hands. And because nobody can go and look, because no experiment we know how to build can reach inside a horizon and send us a postcard, these are genuine guesses, educated and careful and mathematical, but guesses. I will lay one of them before you, not because it is proven, it is nowhere near proven, but because it shows you how differently the ending might read once you let the physics of the very small have its say. The guess goes like this. As the collapse rushes inward and the density climbs past anything ordinary, past the density of a nucleus, past densities with no name, there comes a point, long before r equal to 0, where the smear I told you about, the refusal of matter to be pinned, becomes not a tiny correction but the whole story. And at that density, the collapse does not continue to a point. It cannot. The same quantum stubbornness that keeps a single particle from being cornered now pushes back on the entire inrushing mass. A pressure of a kind that has nothing to do with heat or with any force in your daily life. A pressure that comes purely from the impossibility of squeezing that hard. And that pressure, in this picture, is enough. It stops the fall. It halts the collapse at some staggering but finite density, a smallest possible ball rather than a pointless point, and then, having stopped it, it does something no classical black hole would ever do. It shoves back out. The collapse becomes a bounce. And here is the part that catches in your throat, the part that makes this idea more than a curiosity. That bounce, in the star's own reckoning, is quick. If you could ride on the collapsing matter and hold a stopwatch, the whole affair, the fall, the halt, the shove back outward, would take almost no time at all. A flicker, the blink of something that does not have eyes. But you are not riding on the matter. You are far away, standing where the gravity is mild, and between you and that flicker lies the very thing we have been circling all night. The stretching of time. The same stretching that froze your friend at the horizon and would not let them cross, that same slowing, applied now to the bounce itself, smears that quick flicker across an almost unimaginable stretch of outside time. What is a heartbeat for the star could be longer than the present age of the cosmos for you and me. So the bounce is real. And the bounce is also from where we sit, so slow that we would swear the thing just sits there, black and patient and permanent. The white hole that is supposed to spray the matter back out is, on our clocks, still gathering itself to exhale. I want you to feel how strange a resolution that is. We began with a puzzle about a person who seems frozen at the edge, never crossing, and here at the far end of the night, the boldest guess about the very center hands us the same trick again, wearing new clothes. Time dilation at the doorway. Time dilation at the heart. The outside world always sees the drama slowed to a stillness, while the thing itself lives its short violent life in private. Whether that guess is right, I truly cannot tell you, and I will not pretend. It is one road among several. It rests on a theory of gravity woven from tiny loops of space that we have not confirmed, and other honest people have drawn other pictures entirely, and nature has not yet leaned over and whispered which of us is warm. But it is a lovely thought that the singularity might not be a place where physics dies, only a place where physics does something we have never watched it do before, and then recoils. Now let me gather the threads, because we have laid a great many of them across this long dark, and a good detective, before he puts away the file, says aloud what he thinks actually happened. We started with a friend falling, and with your certainty that you would watch them freeze at the horizon and hang there, reddening, dimming, forever. And that certainty was not wrong, exactly. It was true, but it was true only about you, about your view, about the light that had to climb up out of that pit to reach your eye and arrive later and later and wearier until it stopped arriving at all. The freeze was never something that happened to your friend. It was something that happened to the picture of your friend, a shadow that got stuck on the wall while the person who cast it walked calmly out of the room. That was the first turn, and everything after it was the slow admission that the view from outside, which feels so complete, so total, is in fact one of the most misleading vantage points in all of nature. Because your friend, on their own watch, felt nothing snapshot. They passed the horizon the way you pass an unmarked line on a highway in the dark, without a bump, without a sign, without the faintest sense that the world behind them had just sealed. And then, having crossed, they found that the geography had changed under them in a way no map warns you of. The direction we call inward, the road to the center, had quietly stopped being a direction you can choose and become a direction you are swept along, the way you are swept from this moment into the next one, whether you like it or not. The center stopped being a place off in front of them. It became a time up ahead of them. And you cannot decline a time. You can turn your ship around in space, you can fire every engine, you can beg, but you cannot steer away from next Tuesday, and inside that horizon the center is exactly as unavoidable as next Tuesday. That was the true payoff, the thing the whole investigation was walking toward. Not that the center is far, or hidden, or guarded, that the center is not aware at all. It is a when, and when they reach it, the theory that carried us so faithfully all this way, Einstein's beautiful geometry, the geometry a dying man worked out by candlelight between artillery barrages and mailed off in a letter, that theory lifts its hands and admits it can go no further. The curvature it predicts does not level off. It climbs and climbs past every bound toward the infinite, and an infinity in a physical theory is never a triumphant answer. It is the theory's own way of confessing that it has been pushed past the country it knows. Penrose showed us the confession is not a fluke of some too tidy, too symmetric toy problem. Squeeze matter tightly enough to trap the light around it, and the singularity must form. There is no clever asymmetry, no lopsided collapse that lets you dodge it. And then he and Hawking turned that same lantern around and pointed it backward down the corridor of cosmic history, and found the identical shape of trouble waiting at the very beginning, at the birth of everything, so that the thing at the bottom of a black hole and the thing at the dawn of the universe may be, in the deep grammar of the equations, close cousins. We peered as close to that bottom as the mathematics would let us, and instead of a serene, silent point we caught rumor of a storm, the chaotic churning that the Russian physicists imagined, space itself stretching one way and crushing another and then swapping, over and over, faster and faster, a wild oscillating dance in the last instance before the end. We are not certain that dance is real. It lives on strong evidence and shaky proof, which in this business means it is a serious idea and not yet a settled one. And then, right at the edge of the knowable, the quantum suspects stepped forward with their oldest and simplest objection, the one that says you may not corner a particle into a point no matter how hard you push, because a particle is not a dot but a smear, a spread out reluctance to be located, and from that reluctance some have built the bounce, the Planck star, the black heart that is not a point but a smallest possible ball, holding its breath across an eternity of our time. So which is it truly at the exact center? A tear in the fabric where questions themselves dissolve? A frozen bounce waiting out the ages? Something none of us has yet been clever enough to dream? Here is where an honest man stops and refuses to sell you a certainty he does not own. We do not know. We have never seen it. We cannot see it, not with the finest instrument ever built, because the horizon is a one-way curtain and nothing that learns the answer can carry it back out to us. The photographs we do have, the great orange rings that the telescope spanning the whole Earth assembled, the one from the heart of that distant giant galaxy and the one from the middle of our own Milky Way, those show us the doorway, the bright hot matter swirling at the lip, the round dark silence where the light bends away and does not return. They are the closest look we will ever get, and they show us everything except the one thing we most want to see. They show the shore, they do not show the bottom of the sea. And maybe that is the truest note to end on. For 100 years now we have chased this question with pencils and with proofs, with dying men's letters and living women's equations, with theorems and telescopes, and we have learned something genuinely astonishing, which is not the answer but the shape of our own not knowing. We have learned that the freeze was a trick of the light, that the fall inside is gentle and brief and utterly certain, that the center is a moment and not a place. that our best theory of gravity is also a theory that tells us precisely and honestly exactly where it stops being true. It is a rare and grown-up kind of knowledge, to hold a map and to know, drawn right there on the map in the mapmaker's own hand, the small region marked here the map is wrong. Most of what we call understanding is really just knowing better where the edges are. So think, as you drift off, of your friend still falling. On your clock they are frozen at the rim, a faint red smudge that will fade so slowly you could watch 1,000 lifetimes and never see it wink out. And on their clock they are already gone, already across, already swept toward a moment that arrives as surely as morning, into a place our finest minds can describe right up to the last breath before it, and then can only fall silent and wonder. Two true stories about one falling person, and the space between those two stories is the whole mystery, and we live, all of us, always, somewhere in that space, holding a clock that only ever tells us the truth about ourselves. Good night, and may your own falling tonight be soft and slow and long.